Hey, hallo. Iedereen, daar ben ik toch weer. Hebben jullie mij een beetje gemist?
Is wel zacht.
Ja, maar ik weet, ja, waarschijnlijk gaan mensen natuurlijk zo spreken naar iedereen en allemaal dingen vertellen op het scherm. En dan zo. Zien jullie? Oh. Ja. Ik was van de week toch aan het wandelen buiten. En wat denkt u dat ik zie?
Dit gaat naar YouTube, hè?
Oh, ja. Goedeochtend iedereen.
Ja.
Ja, moet ik verder nog iets vertellen of denk je...
Nee, hij staat aan en hij doet het. Nou, alleen Frankie zijn room nog.
Wat heb je?
Frankie.
Frankie?
Die er net niet was. Frankie. Ja. Moeten we die dan wel even uitzetten voordat als er iemand... Dit is eigenlijk 0.
Ja, daarom zet ik hem juist iets zachter.
Nee, dan moet je hem daar even iets zachter zetten.
Ja, dat is goed. Zet hem hier wel op 50.
Nou, dat mag wel harder.
Maar is dat niet gewoon lijn, dat je hem hier nog met een pad terug moet duwen?
Ja, maar hij komt hierop binnen.
Oh, hij komt daarop in.
Via de HDMI.
Nee.
Of was dat de USB?
Dat weet ik niet.
Huh?
Dat is USB.
Dat was de USB.
Dat is USB.
Oh.
Dat is,
Je kan het hier ook nog levelen, hè? Als je wil.
Nee.
Ja, maar dan komt iemand met een andere laptop en dan...
Ja.
Ja, zo is het beter. Ja. En doen we eens op HDMI dan?
Test, test.
Test 2.
Hello? Oh. Hello? Hello, welcome to the first parallel session for JuliaCon. Our first speaker is Wolfhard Feldmayer from University Hospital of Vienna, and he will talk about differentiable rasterization of point cloud data. The floor is yours. Have fun.
Thank you, and also welcome from my side to this session. So this talk is about the package called diff point rasterization, and this is a new package, my first one actually. It will end up in the general registry hopefully today, if all goes well. And as the name suggests, the package is concerned with the rasterization of point clouds in a way that is fully differentiable. So what do I mean with that? What do we mean by a rasterization of point clouds? So you basically have a set of points and you have a raster. So a raster is a regular rectangular grid in this case. So for example, in 2 dimensions, that would just be an image consisting of pixels. In 3 dimensions, you would have voxels and so on. And then for each point, you just find the correct bin and add the point's weight to that bin. So this example here shows the process basically. So you have a point cloud in yellow, an airplane that is 3-dimensional. You project it down to 2 dimensions, and then you put it in this very coarse raster for this example. So this is a 64 by 64 grayscale image. You basically fill the pixels with those points. So this process is basically just discretization of position information with maybe some projection in between. So almost by definition, this is not differentiable, right? It's discrete. It's not even continuous. So how can we deal with this? We can make it continuous like so. So consider a single point as shown in blue here. Normally with normal rasterization, you would take this point and just fill a single pixel with the point's weight. So in this case, this would fill the center pixel here. But what we do instead to make this continuous is we consider the nearest neighbor pixels. So we take the 2 to the power of n pixels that are closest to the point, where n is the dimension of the grid. In this example, we are 2-dimensional, so we have 4 nearest neighbors. And then we simply do a multilinear interpolation. The closer the point is to the bin center, the more weight it gets. If point and bin center fully overlap, then a single pixel still gets all the weight. So for this example, the resulting part of the image filled by this blue point then looks something like this in grayscale. As you can see, several pixels are now affected by a single point, and now it is continuous and actually piecewise differentiable. So just as a quick side note, so the effect of a single point is still very localized, so especially for very fine grids. So if you might want to follow up with a blurring operation, so individual points can feel a gradient from further away. Okay, but so how can we use the package to do this sort of thing? essentially a package offers a single function as an API. It's called raster, and it has several arguments. The first one being the size of the output grid. This is just an n tuple of integers. So if this is a 2 tuple, then you will get a 2-dimensional image. If it's a 3 tuple, you will get a 3-dimensional image, and so on. Second is a vector of points, where each point is itself represented as a vector. And this is followed by parameters for an affine map. For example, this could be a rotation matrix and a translation vector. But it doesn't really have to be a rotation matrix, can be any matrix, and it doesn't even have to be square. So for example, you could also provide a rotation matrix multiplied with a projection matrix. The main point here is the dimensionality input as well as output is really arbitrary as long as this is consistent. So meaning basically if you put in an m-dimensional point cloud and your output should be an n-dimensional image or grid, then this linear transformation R needs to be an m by m matrix. That's all. Okay, so let's look at a quick example. So we want a 3-dimensional output that has 64 pixels in each dimension. So we plug in a 3-dimensional point cloud, our airplane here. So we need a 3x3 matrix. In this example, this is just a rotation matrix, and then we end up with a 3-dimensional image, image consisting of voxels. We can use the same point cloud as an input and raster it into a 2-dimensional image. So therefore, we just provide a 2 tuple as the size. But now we need to provide a matrix that projects down to 2 dimensions. So we basically pre-multiply this rotation matrix with a projection matrix, and then the output is a single image, very low resolution. Okay, there are other parameters that are optional, such as a weight per point. Then you can provide a background value per image and a weight per image. And I said per image here, but so far the output has always been a single image. So what's going on here? There's also a batched mode. So if you provide vectors of parameters instead of just a single set of parameters, then the output will have an additional batch dimension in the last position. So it has a trailing batch dimension. And of course, these vectors all need to have the same size. In this example, the length is 9. So you will end up with an array that has length 9 in the last dimension, basically representing 9 different images corresponding to these 9 different camera parameters, if you will. If you use batched mode on CPU, things run in parallel over different threads. So each image basically is running on its own thread, as long as there are enough hardware threads available, of course. On GPU, all points actually rastered in parallel. Okay, so far I've talked about the forward process, but as advertised earlier, the way the rasterization is done is differentiable, and it's actually differentiable with respect to all parameters, or at least with respect to all continuous parameters, all parameters except the first one, the size. So how do you actually use this in a differentiable program, right? So if you use a chain rules compatible automatic differentiation library, you don't worry about this at all. It just works. So you just use the raster function in your forward pass, as shown in this very simple example, which has a quadratic loss that uses the raster function in the forward pass. And then the reverse diff rules that are included in this package take care of the rest. So the AD system recognizes the reverse rules and basically provides you with the backward pass. And then you can access, like this example shows Zygote, right? You know how to use it. You can then access a gradient of this scalar loss functions with respect to the input parameters like so. But there is also an explicit interface. So if you don't want to use automatic differentiation, and again, the interface consists of just a single function. It's called raster pullback. Done? It's called raster pullback. It looks like this. It takes the exact same set of arguments as the forward pass, but instead of the first argument being the size of the output, it takes the sensitivities of a scalar value with respect to the output of the raster function and pulls them back and returns the sensitivity of this scalar value with respect to the input parameters of raster. Okay. Yes, please.
Why did you choose to do this affine transformation for the user and not let the user decide what to do with points before throwing the points into your function?
Well, so the true answer is because, I mean, I used that in an application and I want it this way. But I also think, so, I mean, I want gradients with respect to, you know, this linear transformation and the translation.
Yeah, but
So
then it would be 2 lines of code in your loss function, right? So that would still be possible, or not?
Maybe I don't fully get the question. Can you maybe
So you apply this affine transformation, RNT,
inside this function? Yeah.
inside your function.
So you would do it outside.
Yeah, you
is what you're
could also
saying.
do it
Sure.
outside and give your transformed function. So users could choose to do something else.
True. But yeah, so the thing is, so if you want to do this in a batched manner, right, then you will apply different transformations, and it's more memory efficient if you just provide a single set of points and a set of transformation parameters. Otherwise, you would, if you want to do this in a batched manner, then you would have to, you know, transform the whole point cloud in different ways.
Okay.
Yeah.
Thank you.
Okay. Thanks.
And our next speaker is Eric Faulhaber, and he will talk about Julia for particle-based multiphysics with trixieparticles.gl. Please join me in welcoming the speaker with an applause. So the floor is yours.
All right. Yeah, so my name is Eric Faulhaber. I'm a PhD student in Cologne, and I'm going to present this talk together with Niklas Neha. He's a PhD student in Stuttgart, and he's going to take over for half of the talk. All right, so we're introducing Julia for particle-based multiphysics with trixieparticles.jl. So yeah, first I'm going to give a short introduction. Okay, great, you can see my mouse. A short introduction on particle-based methods, explain to you how you can get started and use trixieparticles, and then I will talk a bit about neighborhood search and GPUs. Then Niklas is going to take over and talk about complex shapes and real-life applications. All right, so what is trixieparticles? As I said, it's a framework for multiphysics simulations. It's implementing particle-based methods, and the goal is to be accessible and extensible for quick prototyping. But we don't just want quick prototyping, we also want to simulate real-life simulations, so we also want to have performance to do that. And of course, it's open source and written in Julia. All right, so a quick introduction to particle-based methods. So to make this clear, we're not talking about particle physics, we're not talking about molecular dynamics. It's numerical particles, so basically interpolation points, to do things like fluid simulation or structure mechanics, so it's not related to particle physics. Here's a comparison between two methods. So here we have the discontinuous Galerkin method, DG method, which is a grid-based method. Here we store data in fixed points. So we have these fixed interpolation nodes, and at each of these nodes we have a data value, and together we will get an interpolation by polynomials. Then on the other side we have the smooth particle hydrodynamics method, SPH, which is a commonly used particle-based method. And yeah, here we store data in moving points. And because we cannot just interpolate by polynomials then, instead we use a kernel function, which looks something like this, so like a Gauss kernel. And in order to interpolate a quantity at some point I, we will loop over all neighboring particles, sum up their quantities, weight with a kernel function in order to get the interpolation. Usually these kernel functions come with a compact support because, well, particles that are further away usually have a very small influence, and by cutting the kernel function at some point, we get a small amount of neighbors, so this is for efficiency reasons. And this year, on the left, the grid-based methods, this is an Eulerian approach, so you basically have a fixed grid and the fluid is moving past the grid, whereas on the right, we have the interpolation points moving with the fluid. So let's go into a little more detail about SPH. So as I said, no particle physics, we're actually discretizing the Euler equations. So this first equation here should look somewhat familiar to some of you. This is the momentum equation of the Euler equations. So this is a material derivative here, which is consistent with the Lagrangian approach, a co-moving approach. And this here is discretized in the most basic SPH formulation to this equation here. So what we get here is, instead of having a material derivative of some quantity V, instead we have the regular derivative of a quantity VA. And VA is the velocity of particle A. So here we had a partial differential equation, and we do a semi-discretization, so now we get a system of ordinary differential equations. So the derivative of VA, which is the acceleration that particle A experiences, is given by summing over all neighbors. And then we get this factor here. This is the mass, the sum of the pressures, product of the densities. And this here is the gradient of the smoothing kernel that I showed earlier. So how does the gradient look like? Well, it's proportional to the difference in positions. We call this RAB. So it's just position A minus position B. And this here is just some usually positive scalar. That means that the acceleration that particle A experiences from particle B will be repulsive. So it will just go in the opposite direction. To show this on a quick example, here we have 9 particles. The color denotes the pressure. So we just have a pressure gradient in x direction. This is low pressure, this is high pressure. And if we look at the particle in the middle, this will, as I said, experience a repulsive force from the particle to the left. So an acceleration towards the right. Same with these 2 particles, just a little less acceleration because they're further away. As I said, it scales with the distance. And these 2 particles have higher pressure. So here this term is getting larger. So we have more acceleration. And from the red ones, even more. So the resulting, we now sum over all of these particles, and the resulting acceleration will point towards the left, which is consistent with the physical behavior. Particles are moving from areas of higher pressure towards areas of lower pressure. Okay, so that's enough theory for now. What can we do with this? How does that look like? So this is the example that you saw on the title slide. It's done with tricksy particles. So as you can see on the right, these are all particles. These are about 10 million particles. And the water is modeled as with the weakly compressible SPH method as a weakly compressible fluid, which means it's using exactly the equation that I showed earlier, well, plus some extra terms. And the rubber ball, so this is an elastic rubber ball, you can see it oscillate underwater, is modeled by a different SPH formulation called total Lagrangian SPH. So with this total Lagrangian SPH, we can also do things like this. This is a very basic example from the literature. We have an elastic beam that is oscillating under its own weight under gravity. And as you can see on the right, we can very nicely reproduce results from the literature. Okay, so why do we use particle-based methods? The biggest advantage is that we don't need a mesh, as opposed to grid-based methods. So we don't have to go through meshing processes. We don't have to mesh a complex geometry. Instead, we basically just fill the domain with particles. Nicholas is going to talk a bit more about this later. The next advantage is that changing domains are relatively easy to handle. So consider this falling ball example. We have a rubber ball which is changing its shape, and then you have a fluid with a free surface which is moving around. So this would be quite challenging to do with a grid-based method. Whereas with particle-based methods, we basically get this for free. We just have the particles interacting with each other. Disadvantages are that well, these methods are low order by design. So compared to grid-based methods, they have a correspondingly lower efficiency. If you can use a grid-based method, and that's the biggest reason why we use particle-based methods, because if we have complex multiphysics with complex geometries, then it's very hard to use grid-based methods. So this is where particle-based methods are commonly used. Another disadvantage is that we have more open challenges. So compared to, say, finite volume methods, which are very well researched, you will obviously have more open challenges. But well, for us as researchers, it's also an advantage. Okay, so how can you use Trixie particles? Okay, first install Julia. I hope everyone in this room did this already. And then you can just install Trixie particles. It's a registered package. You will also need ordinary diffie-q to solve the resulting ODE problem. And if you want to plot the results, you need plots. Then we have an examples directory, where we have a bunch of predefined examples that you can try out. And in the fluid subdirectory, you will have an example called hydrostatic water column 2D. This is basically our basic example. It runs then in less than a second. And then you can just plot the solution by calling plot sol. And then you will get the picture on the left. So you can see that's the fluid, a bunch of particles with a very coarse resolution. And it's inside a tank, which is modeled by boundary particles. So we're using particles, or a particle-based boundary condition here, because it makes it very easy to sample complex geometries. I mean, we have to sample the fluid, right? And then we can just also sample the boundary as well, and we don't have to go through some triangulation process. So Niklas is going to talk a bit more about this in detail as well. We also export VTK files, so you can just load them straight into ParaView or a different tool, and then you can, for example, see this hydrostatic pressure gradient. If you want some cooler example, you can use the dam break 2D example, which will run this 2D dam break. And yeah, so let's go back to the theory and to the neighborhood search. So as I said, we have a compact support, so particles only interact with neighbors within this compact support. How do we get those neighbors? That's where the neighborhood search comes in. So we need to find neighbors within the compact support, which is usually fixed for these methods. So we have we model weakly compressible fluids and structure mechanics. For these, we have a fixed search radius. And we don't just have to find the neighbors, we also have to update this in every single time step, because, as I said, particles are moving. So for this, we use a grid-based neighborhood search. So for example, to find the neighbors of this particle here, we just put a grid over all the particles, where the grid size, the cell size is exactly the search radius. And then in order to find all neighbors, we just have to loop over the neighboring particles and consider all of these potential neighbors, and then determine which of these are actual neighbors. As you can see here, all of these outside are not potential neighbors. So even if there are a billion particles, this will still take the same time. So this gives us neighbors in a constant time, which is obviously much more efficient than looping over all particles in the simulation. Yeah, so the neighborhood search is basically the most important ingredient to get performance with these kinds of methods. So we wrote our own package. It's called Point Neighbors JL. It's also a registered package. You can scan the QR code if you want to go to the GitHub page. So it's a package for neighborhood search with fixed search radius. We focus on fast incremental updates. And the goal is to be like a playground for trying out different implementations. So you can very easily switch data structures and implementations. But it's not just a playground. So we also use it basically as our main neighborhood search implementation in the production simulations. So our current development focus is on GPUs, so neighborhood search on GPUs, which is also what we did with Trixie particles in the last few weeks, months. So we implemented vendor-agnostic GPU kernels with a kernel abstractions package, but we're in a very early development stage. So this is the first version that we now have in a release. We had a heavily multi-threaded code, and we basically just replaced the multi-threaded kernels, multi-threaded loops by kernels. So we didn't yet do any choose any optimized memory layout. We didn't do any specific kernel optimizations. These are all plans for the next few weeks. But it's already running on GPUs. And the performance, so here we see the runtime per particle for different numbers of particles and a CPU and 2 GPUs. So as you can see, for small problems, obviously the GPU is quite terrible. But then if it's somewhat saturated at about 1 million particles, we will see a speed up of 2 or even 3 for the GPU. So considering that this is a very basic implementation, this is actually pretty surprisingly good. But of course, these are very powerful GPUs, so we would expect to get more speed up in the future. All right, and now Niklas is going to take over.
So thank you, Eric. In the following, I will talk about how to preprocess data with Trixie particles to simulate like real-life application. And I also want to show with an example that we can indeed, or particle-based methods are indeed well suited for such complex simulations. That is, here we have a motivation, the blood flow to the aorta. So the aorta is the main and largest artery in human body, originating from the heart, branching upwards and extending down to the abdomen. And one would ask, why should we simulate such a problem? So the blood enters the aorta through a valve, and if this valve starts failing, surgeons will probably implement like a mechanical valve, and this might lead to non-physiological behavior. That is, the blood flow could harm the aortic walls. And that brings me to the work of Laha et al. They conduct such an SPH simulation, and they found out that the mechanical valve indeed harms the wall more than the native valve, as you can see here. And I want to point out here that this is not a Trixie particle simulation, and also that I will not discuss any simulation results in the following talk. But I want to point out that we want also reach this goal to set up and simulate such problems. And I will now in the following talk about the preprocessing tool of Trixie particles. So what are the steps to set up such a simulation? So at the beginning, medical researchers will probably do an MRT of this MRT scan of the aorta, and other researchers will then extract from these images an STL, so a 3D STL file, which we then can preprocess in, for example, Blender. That is, we can extrude the inlets and the outlets, and then we have to convert this STL file to our, so to say, input data for our program. That is, we need initial conditions for our systems. And Eric mentioned before that we have to fill, or we just have to fill the domain with particles. And basically, we have to do this. So the initial conditions holding the positions of each particle. But how can we do that? So we have our triangle mesh, which is our STL file. And we load this in our program. And then we pass this shape to the complex shape function, which will return initial conditions. And we then also have to define, of course, the resolution of our problem, so to say the particle spacing, and also the density for each particle. And then we can also define an algorithm for inside and outside segmentation. Per default, we use an winding number approach, which is basically, or which checks basically if a point is inside an object or not. And then we have this grid structure, but what we want to achieve is like this perfect body-fitted sampled initial condition, which we see on the right-hand side. So why do we want to have this? So we want, of course, an equilibrium at the initial state of our simulation. So that is, we use here a physical-driven approach. So we generate a particle packing system in which we pass this initial conditions, and also we define here a boundary, which is basically the triangle mesh. So and then we can create with our framework an ODE, and also solve this ODE and extract from this final solution our perfectly packed initial condition. So what's behind this particle packing method? So basically we calculate for each particle the acceleration according to this formula, which is basically the SPH formulation, which you can see here. And the difference here is that we have a constant background pressure. That means if this gradient here vanishes, we have an equilibrium. And the problem now is that we have to constrain the particles onto the surface, otherwise they will drift away. So that brings me to the surface bounding method, surface particle bounding method based on the work of Xu, which basically update each position of the particles according to this condition here. We have the initial particle spacing, this delta x, and the n is the normal to the surface. And then we have the phi, which is the signed distance from each particle to the surface. And how can we calculate this? We just interpolate for each particle the distance field to the particle, and with a kernel function or with a normal SPH form interpolation. So we can just use our framework for this. And also, as we can see here in this 2D circle example, we only generate this field close to the surface. The field is basically our dummy particles holding the information like the normals and the distances. So that has the advantage that it's, of course, very memory efficient, and also it's fast since only particles close to the surface will interact with this field. Another advantage is that we can also sample and pack boundaries, as Eric mentioned before, that we in SPH usually we represent the boundary with particles. So how can we do that? For the fluid, okay, we just generate our particle packing system, and for the boundaries, we use the same shape, so the same triangle mesh, but we generate another particle packing system in which we define the boundary thickness, and also we set a boundary flag to true and just pack the boundaries, and we have boundaries for our problem. And then we can simulate this. So I simulate here, or I run a simulation which is a fluid flow through a rigid aorta, or basically through a complex geometry. It's not validated yet, so it's just a proof of concept. And we see here roughly about 790,000 particles in total. And I prescribed here a velocity at the inlet, and then the flow or the blood or the fluid leaves the domain through these 4 outlets here. And I run 1 second simulation time, and this took about 45 minutes on an AMD EPIC CPU. So of course we can also run 2D examples. So I liquefied the Julia logo. I basically put the initial conditions of the ladder in a fluid system, and the initial condition of the dots in a structure mechanical system. So what we see here is an an multiphysics simulation or an FSI or fluid structure interaction simulation. So we can see here, once we have the initial condition, setting up a simulation is straightforward. And yeah, coming to an end, what are our future plans? Of course, we want to have more particle-based methods, so we are only talking about SPH, but we also can simulate DEM or discrete element methods, and then we want to couple them. And of course, we want more multiphysics, so like coupling with heat conduction, so you can also model heat conduction with SPH. And then we want, as I mentioned before, we also want simulate real-life applications. What we need for this is, of course, high-performance computing. And of course, our very next step will be optimizing the GPU implementation. So coming again to an end, thank you. And you can find us on GitHub. Thank you.
So is it possible to do this simulation for long-range forces? So if I want to simulate a fluid system collapsing under its own gravity, the forces are long-range. Would it be possible to use Trixie particles?
Well, not yet, but we would be able to implement this. The question is how efficient it would be, because, as I said, the neighborhood search is optimized for short-range forces.
I have two questions, actually. First one is, do you have surface roughness or friction between fluid and the solid implemented already?
Yeah, it's different from like common mesh-based methods. So we have like close to the surface of the boundary, we have like an artificial viscosity, so we can model non-slip or roughness boundaries. So it depends on which level, if it's macroscopic roughness or microscopic roughness. So it depends. Maybe if one is interested in it, one could implement a microscopic roughness with a different modeling or something like that. But we can simulate non-slip conditions.
Yeah, so we basically just apply a viscosity force between fluid and boundary
Okay,
particles.
so no things like surface tension and so on of that.
We have a proof of concept for surface tension, but the model we have currently is not great, let's put it that way, but we're in the process of implementing different beta models.
Okay, let's have a chat later. A second question would be, is the neighborhood search already implemented for GPUs, or is it still CPUs?
We have a first version on GPUs.
Yeah.
If you check out the README of point neighbors, you can see a comparison between different implementations. So we have one that has an infinite domain, so where only used cells are actually initialized. This only runs on the CPU, but then if you have a fixed domain, then this does run on GPUs.
Okay, thanks.
Hello. Is the neighborhood search the bottleneck right now, or is it something else that's bottlenecking the?
Well, it's difficult to say what is the bottleneck directly. It's not like we first query all the neighbors and store them somewhere, and then we do the actual interaction forces. It's basically entangled, so we loop over the neighbors while we do the interaction. But well, since the rest of the code is pretty well optimized, of course, every optimization, most optimizations happen in the neighborhood search. That's just how these things work.
Okay, and the 45-minute simulation there for 1 second, how many? Do you know how many time steps that was, or?
I think it was 40,000 time steps.
So 1,000.
I think 40,000 times.
Okay, so 1,000 per second. I
Yeah,
guess.
yeah.
Okay.
You can find numbers per or times per time step on the point neighbors README. There are plots, numbers times per particle, but then we have benchmarks for a single right-hand side evaluation of the time step.
Okay, thanks.
And note that we use higher order time integration, so the time steps would be different for low order.
Thanks, great talk. How does the features of the neighbor search compare to cell list map, for instance? Can you do periodic boundary conditions, minimum image convention, that kind of thing?
That's a very good question. So cell list map.jl is using a similar method. So now that we implemented the fixed domain neighborhood search that I mentioned earlier, this is very, very similar to the implementation in cell list map.jl. We do have similar performance, but we don't have these complex boundary conditions. But we now have, as Nicholas said, we have inflow and outflow boundaries. So far we didn't have the need to implement complex boundaries. But note that point neighbors is also meant as basically an API wrapper. So we do have a pull request to implement a backend using cell list map.jl. So it would be easy to add the boundary conditions to that, so that one can easily use cell list map as a backend for Trixie particles.
Okay, time to move to the next speaker. If you have further questions, please chat during lunch. Let's thank the speakers one more time. Yep. And our next speaker is Ken Fisher, and he will talk about Cheddar ID, a new tool for next generation circuit simulation. The floor is yours.
Excellent. Okay, let's get started. I think people will probably filter in because we are 30 seconds ahead of schedule. This never happens, so thank you very much to the volunteers for keeping us on time. So I think what I'm going to do is I'm going to do the live demo first. So people who came here early get to see the live demo, and then people who get late still get to see what it looks like. So this is Cedar, our analog circuit simulator. So this is simulating a CMOS inverter in an ASIC. In particular, this ASIC technology is. Oh, can people hear me on the microphone, or do I need to sit?
It's up to you.
Okay. I kind of like standing while speaking, so I will use the microphone. Hello, YouTube. Also, my apologies if you missed the first part of that. So we're doing the live demo first, just to give people a chance to get all the way up here on the to the 4th floor. But so yes, so this is Cedar. This is simulating a CMOS inverter, very simple circuit in. Sky 130 technology, which is the technology that Google open sourced. So you can tape out your own chip using this using the semiconductor technology and use Cedar to simulate it. And this is a live demo, and this is just a parameter exploration, and it's showing some of the things you can do. This is validating that this is validating that the inverter satisfies its design requirements. All right, come on in. I'm just doing the live demo early so that people have something to see while we wait for everybody to come. But we do have a full program, so I will get started shortly. Okay. So much for the live demo. Let's go to the actual talk. Increase the font size. I don't. Oh, in the live demo. Yes. Okay, this is not really designed to be shown on a screen this small, but good. All right, let's go to the actual slides. Okay, welcome everyone. Welcome to those who just came in. So I'm going to be talking about Cedar. I think I first probably need to start with a quick glossary. Cedar is pretty big as a project, so there are several terms that you may hear which refer to very specific things, but sometimes can be a little bit confusing. So Cedar is everything we're talking about, all the packages, all the packages and the product, everything. Everything you're about to see is Cedar. There's also Cedar EDA, which is a particular distribution of Cedar, specific versions of all the packages, as well as some integration into the Julia Hype Cloud platform. So that's Cedar EDA. There's Cedar Waves, which is the plotting and analysis thing that you saw in the live demo, the little widget on the right-hand side. There's Cedar Sim, which is the actual simulator. And then there's DAE compiler, which I'll be talking about some as well, which is the core compiler technology that is powering Cedar. So for this talk, I want to focus mostly on Cedar Sim and DAE compiler. It's a little bit different from what I promised I would do in the abstract. Some talks got consolidated, and I also already gave a previous talk about some aspects of Cedar at LatchUp, so I wanted to not be too redundant. So if you're more interested in using Cedar as an end user, I think the LatchUp talk will probably be more interesting to you. The link is on the slides. But what I want to talk about today is how does Cedar work under the hood, how is it implemented, and in particular, how are we leveraging Julia in the implementation of Cedar. So I think Cedar is different things to different people. It is, of course, a high-performance SPICE-compatible analog circuit simulator. So, for people who are using things like Spectre or HSPICE or AFS or open-source simulators like ngSpice or Zeiss, in the fullness of time, you should be able to just use Cedar as a replacement for a simulator like that. But Cedar is more than that. You can think of Cedar as an implementation of multiple programming languages common in this domain, Verilog A and SPICE in particular. You can think of Cedar as a technology demo for using the Julia compiler technology to apply it to other programming language. You can think of Cedar as the reason we have effects, exception types, semi-concrete evaluation, optimized generics, and a bunch of other goodies in the Julia compiler. All of those are not Cedar specific, of course, and some of those were ideas that existed before Cedar. But Cedar was, Cedar was the reason that we ended up actually implementing them in the Julia compiler. It's implemented as a set of composable packages, as is common in the Julia ecosystem. So if you want to build something that's not quite a circuit simulator, but needs to interface with data structures from this domain, needs to interface, needs to do something with circuits, you may be able to just reuse part of the Cedar stack for what you want. And it's very deliberately kept as separate and independently usable Julia packages. Lastly, there's a little bit of an exploration for what high-level synthesis might look like in Julia. I'll touch about that a little bit. Some of you may remember the FPGA demo I did at JuliaCon in Baltimore 5 years ago. So this is a little bit more evaluation on that thinking, and we'll be doing more thinking on that over the next year or so. And lastly, it's on GitHub. It's mostly MIT licensed. Some parts are CERN OHL SV2. If you're interested in why that particular license choice, also see the other talk where I dive more into the motivation. I will caution that I have not fully completed opening up the repositories yet, so the version that's on GitHub is probably not usable for actually using it, but it is certainly usable for reading the code and following along. Okay, so you saw this diagram that Viral used a Photoshop version of this morning in the sponsor talk. This is the architecture diagram for the compiler parts of Cedar. Basically, we take in these modeling representation SPICE Verilog A. We compile them into general purpose IR. Then we do some optimizations on them, both structural and ordinary compiler optimizations, and then we code gen them for the numerical solver. But I think it's more interesting than the architecture diagram is how this maps to various Julia packages. So a core aspect of how Cedar is designed is that we reuse core.compiler, the core Julia compiler infrastructure, as much as possible. So all the IR representation, all the general purpose optimizations are just core.compiler. AD is just diffractor. And obviously, we're using SciML for the solvers. We're using the stage selection code that's in MTK. Where exactly that will live is a bit of a TBD, but it's the same code that's in MTK and JuliaSim compiler. So the pieces that are sort of different are the language support for Spice and Verilog A, which sits in Cedar Sim, and then some of the code generation at the bottom, which is in DAE compiler. All right. So let's talk about DAE compiler. But first, let's talk about why does DAE compiler exist? We have an amazing ecosystem for solving differential equations. What does DAE compiler do that the rest of the ecosystem does not? And the point I want to start is the raw diffieq.jl SciML base interface for solving DAEs and ODEs. So for those of you not familiar, you basically specify your system as a Julia function, which evaluates the differential algebraic equations, puts the residuals in an output array, and then you can give this to SciML, pass it to the solve function, and all of the hundreds of solvers that SciML has will just automatically work on for your function and will give you appropriate results. And this is a great interface, right? Like it's extremely simple. It's extremely explicit. It'll just run the code many times inside the inner loop of the solver. It'll run exactly what you give it. It'll do AD the standard way to give you Jacobians if the solver is needed. So I'm actually like, I think this is a great abstraction, and it's more powerful than the abstractions that you have in a lot of traditional simulators. So already this is better than the things that traditional Spice simulators, for example, are built on. But there's some problems with it also. So I think the biggest problem is that we don't have the structural transformations. So all of the optimizations that were in the slide blue on the right-hand side of my architecture diagram, those are not applicable. It just treats the system as a black box. There's lots of explicit indexing in this, so you sort of manually need to keep track of where are my states, where are my derivatives. Partly for that reason, and also for some other reasons, it's not super easy to compose and reuse smaller systems. You might hear me say this representation is non-operatic, which I won't dive into, but there's some mathematical theory on how to compose these systems. There's things like event management and discontinuities, which you need to do manually here. It doesn't track states and parameters other than through indices, and it's also not completely universal over all solver types. So while it's mostly universal, there's still like 3 or 4 different representations that you may have to write manually, and you also have to do, as I said, things like events and discontinuities manually. So it's great, but not perfect. So why not just use MTK? Wasn't MTK supposed to solve exactly this? And partly yes, so it does automatically paper over all of the solver abstractions for you. So it generates all of the different representations of the system for you that the solvers want. It has state and parameter management, and it's a much higher level representation, and it has all of the optimizations and the code gen and all of the nice things that I wanted. It's built on symbolics, so it's more of like conceptually it's more of a symbolic programming framework, and that comes with a lot of choices and to my mind at least, drawbacks if you're trying to use this as a compilation target for a higher level modeling framework. So there's a lot of global state. Things are indexed, things are identified by the name of the variables. There's lots of global variables. And even if that doesn't bother you, at the very least, the semantics of MTK code are not Julia semantics. They're MTK semantics, and there's some embedding into Julia semantics, but it's something that you have to learn at the very least. MTK doesn't support any explicit control flow, so MTK models are traced out of the Julia representation. They're not compiled. So if you have an if statement or a for loop, those get evaluated eagerly. They don't get delayed into the model. There's some support for pre-compilation by writing out the generated Julia file and Julia code, putting it in a file and pre-compiling that. But it's not as seamless. You have to sort of do it explicitly. And I think most importantly, it's too slow. So Cedar did actually start out as an MTK frontend, but we ended up having to do something different to support the size of models that come up in the semiconductor domain. So next question, if it's too slow, why not just use Julia Sim compiler, which is MTK, but implemented better, so it's faster. It's a good choice for making things fast. But from my perspective, it has a custom compiler stack, fully custom LLVM code generator, fully custom IR representation. It still inherits MTK's semantic representations, so the semantic challenges that MTK has still apply to Julia Sim compiler. And now you have two compilers, and I'm already struggling to maintain the Julia one, so I didn't want to maintain another one. There's also some issues around parameter specialization and generating specialized code for different choices of parameter sets, which is a little bit in the weeds, but these semiconductor models are not only large, but they're also parameterized by thousands of parameters. So if you have thousands, tens of thousands of transistors, your models easily have millions of parameters that you may want to manage, which is not a domain that, at least at the moment, works well in MTK. Also, Julia Sim compiler is newer than DE compiler. So even if I wanted to use it, I couldn't have because it didn't exist. Okay. So now that I've talked extensively about what DAE compiler isn't, let's talk about what it is. So DAE compiler is a way to represent systems of differential algebraic equations as plain Julia code plus a small number of custom intrinsics. So the evaluation semantics are basically standard Julia, but with a non-standard evaluator, sort of similar to the GPU stack. So there are some parts of Julia's dynamism that you can't use, but in general, it's supposed to behave as much as possible like standard Julia code. You can kind of think of it as taking the raw diffq.jl representation and just doing the minimal tweaks to it to enable the structural optimizations and to enable this operatic composability. So a core design goal is to reuse the Julia compiler as much as possible, reuse existing packages in the stack as much as possible. I think right now DAE compiler is about 3,000-4,000 lines of Julia code. I'm sort of hoping that in the medium-term future, a DAE compiler with the feature set that it has right now could be maybe written in 1,000 lines of Julia. But we'll have some work to do to get there. It does all of the same optimizations and code generation as MTK and Julia Sim compiler. For DAEs, MTK supports some other system types, but for Cedar, we're mostly interested in DAEs, so that's what it focuses on. It integrates natively with precompile caching, so it caches optimized. It caches the generated code as optimized versions of your model function, just as ordinary Julia caches, native code as optimized versions of your ordinary Julia functions. So that all happens transparently under the hood. It scales to the large models we have in the semiconductor domain, but it is still a modeling domain agnostic tool. So a quick tour of all the intrinsics. So the first intrinsic you have is variable. It just declares a variable. The identity of the variable is the same as the identity of the Julia value that it returns. So while you can give these names, the names are non-semantic. So that's nice for people who already know Julia and know Julia scoping rules, know the rules for how Julia values propagate. They don't have to learn a new system for a second order system for scoping of variables. So it feels very nice to use variables. There's equation bang. So what does equation bang do? Basically, equation bang forces the choices of the variables to be such that the argument to equation bang is 0 or 0 to within solver tolerance at every time step. So it's basically a way to add an equation to the system. And again, the semantics of this are operating through the side effect of the equation bang call, rather than having some other semantics. And the scope / the name of it is again non-semantic. There's also DDT, which exposes total derivatives with respect to time. Under the hood, this uses diffractor, so it has full integration with things like chain rules, so you get all of that automatically. You don't have to manually specify derivative rules for this representation, you just inherit that. There's 5 or 6 other intrinsics for things like partial derivatives, observables, time, discontinuities, but I won't talk about those. If you're interested, you can read the doc strings. So how is this implemented under the hood? As you might imagine, there's a generated function which does some magic. The details of how this is implemented are actually still in flux. This is sort of the whole topic of compiler plugins, and we're still fully working out how those interfaces work. But basically, there's a generated function, and if you give it a Julia function that complies with this modeling representation, uses these intrinsics, it will trade that for a DAE function type, which is the SciML base object that you can pass to solvers to integrate the DAE problem. So semantically, this is reasonably fast at runtime, but it hooks into the compilation stage. So the first time you run this, when ordinary Julia call would do inference and LLVM compilation, this will do the optimization of the DAE system and the code generation for the solver. So yeah, as I said, the exact details of how this works are in flux, but eventually it maps down to a custom abstract interpreter. The details of how that works are extensive and split over multiple talks. So 2 of those already happened, so I'm sorry, you'll have to watch them on YouTube. But basically, what does the custom abstract interpreter do? It provides models for the custom intrinsics that we talked about. So it explains to the Julia compiler how those work. It sets up the caching. It wraps the abstract interpreter that's in diffractor to provide AD support. It has a custom interprocedural analysis. So we added a hook in the Julia compiler, which is used by escape analysis for doing post-inference interprocedural analysis. And this uses the same mechanism. And then it has the custom code generation to generate the various forms that the solvers need. And again, if you're interested in how exactly to do any of these things, there's full talks on basically all aspects of this. A quick look at the custom lattice. So there's a custom lattice element called incidence, what does incidence do? It basically tracks for every value in your function which variables does it depend on. So it explicitly tracks linear combinations with constant coefficients, and then it tracks also which variables it depends on non-linearly. So it might say, okay, this value in your system is a plus b plus some nonlinear combination of c, d, and e, and then it uses that to generate the information that feeds into the structural optimizations. Some other lattice elements also, EC for tracking equation identity, partial scope for symbolically representing the hierarchy of the naming metadata, and then there's partial key value, which is a lattice element to optimize core.generics.key value, which is part of the implementation of scope values. So I think Valentin might talk about that in his scope values talk. Of these, I think all about partial key value are specific to DAE compiler. Partial key value might be moved into base at some point. So what does it do with all of that information? Well, it does these structural transformations. This diagram is not really meant to be understood. It's more for eye candy. But basically, all of the circles are variables, and the red ones are which of these variables does it actually need. So even though the system, and this is the same inverter system that I showed at the beginning, even though it has like 20 variables or so, the structural transformation can see that numerically it actually only needs 3 of them. All of the other ones can be expressed as some expression of those 3 variables. So it reduces the size of the system from 20 variables to 3, which is same sort of transformation that MTK does. Okay, 2 minutes left to talk about CEDAR, 1 minute left. I'll cut maybe into the question time a little bit, so I said the transistor models are large. What do I mean by large? So this is the implementation of one transistor. This is BSIM4, which is a transistor model from the early 2000s. It's about 3,500 lines of code, which is quite a bit larger than even relatively large models for complete systems and other domains. So this is part of the reason why it has a custom compiler stack, is just because of the nature of these models. So all of these 3,500 lines of code define 3 equations in terms of number of equations in the system. So these models are sort of large in number of code, number of lines of code per statement, but not in number of equations. So there's sort of multiple scaling domains. And if you go to the Julia Sim talk, they're mostly talking about scaling in terms of number of equations. But there, each equation is much simpler. So here, each equation is many thousand lines of code, which is a little bit of a different domain. In general, these models are written in a language called Verilog A, which has some superficial syntactic similarity to Julia through various kinds of Pascal-derived languages over the years. But it's an extension of Verilog, the language for specifying digital circuits. It has 2 data types, integer and real. It has a C-style preprocessor, unlike Julia. It has language-level intrinsics for AD. A little bit ahead of its time there, since it's from the early 2000s. I think AD didn't really become popular as a concept until deep learning. So a little bit ahead of its time. It has language-level constructs for these equation and variable intrinsics that I mentioned, and was originally designed to be transpiled to C. So how do we implement this? And I know I'm out of time, so I'll go through this quickly. Basically, the core idea here is that we think of Verilog A as just a very weird way to write Julia, or a string macro. So basically, we have a custom front end, but after lowering, it emits Julia, lower Julia IR, and you get a lot for that. You get LLVM codegen, you get GPU support, you get revise working, you get debugger. Debugger screenshot on the previous slide. You get precompiled, you get caching, and you get all of this in about 6,000 lines of Julia. So for comparison, is that a lot, is that a little? There's a Rust implementation of Verilog A, very recent, about 70,000 lines of Rust, which I'm not making any claims about like Julia versus Rust, and I'm not making any claims that these have equivalent functionality. I'm just saying this sort of semantic domain has complexity on the order of tens of thousands of lines of code, but because we reuse Julia for everything after the front end, we can do it a lot quicker. Similar story for Spice, although Spice is a mess. I won't really talk about it. The one thing I will point out is that we can reuse the Julia package manager for PDK distribution, which is very cool. And the last thing I want to talk about, and this is my last slide, is, if all of these languages are such a mess, can we just use Julia for specifying these circuits directly? And the answer is maybe, kind of, would be cool. This is a way to specify, Cedar has a way to specify circuits directly as Julia code, and in particular, something that you can do is specify parameterized circuits and do parameter exploration, with things like parameterized structs or for loops to generate arrays of things. I hope to talk about that more next JuliaCon. All right, that's my talk.
In the past, modeling
Can you say it for the mic?
Yeah, I'll just repeat the question in the interest of time. Is there an estimate for speed up over modeling toolkit? So I didn't do any direct benchmarks against modeling toolkit, mostly just because modeling toolkit is just not able to do the models that are of interest in this domain. You could obviously use this stack for so we have a way to import MTK models, so you could just run this stack over regular MTK. You'd probably get performance about similar to JuliaSim compiler. So if you look at the JuliaSim compiler benchmarks, probably roughly similar. But DAE compiler exists just because the size of the models is beyond what MTK can do. So there was no point running MTK because it just runs out of memory. Yeah. Yeah. Next question. And I think the next speaker can set up while I take questions. Any more questions? Somebody has a USB-C adapter, I believe. All right. I see no more questions, and I see people running to the next talk. So thank you very much. Thank you very much for making it up here all the way to the 4th floor in the corner of the stadium. I know you have a choice with all the 8 tracks going on. So thank you very much for coming to mine, and I will hand it over to the next speaker. Talk about very cool JuliaSim things.
Thanks. Yeah, yeah. Oh, yeah. Okay. I know it doesn't go full screen. Okay. So I'm going to talk about JuliaSim batteries. So what JuliaSim battery is a product from Julia Computing, Julia Hub, sorry, for stimulating advanced battery models. So we have partial differential algebraic equations for electrochemical models for battery cells. These models are discretized with finite volume methods, and we have several models with different degrees of precision, starting from the most precise one to less precise models with certain assumptions. This, if look at here, I don't know if my mouse can be seen, it's like the equations that we are solving. So these partial differential algebraic equations are discretized into, is my, I don't think you can see the bottom of the, oh. No, it doesn't work. I can try refreshing them. Nope. For some reason, F11 doesn't. Okay. Is this better? Yeah, I think you can see the bottom of the, yeah, okay. Okay, so we have the discretization, so we have like 300 DAEs per each cell, and we can compose these cells into packs, so you can have large battery packs, and one of the advantages of competing tools is that we are much faster than similar tools in Python, for example. We also have thermal and degradation submodels. And also we support different sets of battery chemistries. And it's also easy to add your own chemistry if you need.
What chemistries do you support?
So the ones listed here, NMC, LFP, and LCO. I'm going to show a demo bit in a bit. Okay, and next. So some of the challenges in modeling lithium-ion batteries are the fact that there is a large cell-to-cell variation. So in a battery pack, you have a lot of cells, and there is a large variation in the behavior of each cell. And there are a lot of approaches where you have a one-size-fits-all approach, but this doesn't work very well because of this large cell-to-cell variation. In this plot, we have the degradation with the cycle number, and we see that the degradation for individual cells in a battery pack depends on which cell it is. So there are some cells that degrade less than others, and there are several reasons for this, which I'll go in a bit. If we go to accurate electrochemical models, they are traditionally slow to simulate, and also it's also very hard to scale them in packs. So if you have 1 or 2 cells, it's going to be very different than if you're trying to do 1,000 of them. And if you have a slow model that's already slow at 1 cell, if you go it at 1,000, it becomes prohibitive.
Is this also the data you're going to use to train the...
Sorry?
Are you going to train on this data, on the discharge?
Yeah, you can also calibrate. So if you have your own experimental data, it's possible to calibrate and integrate with the SciML ecosystem to calibrate the model for a particular application where you might have your own experimental data. And in that case, you can calibrate to your specific needs. So the battery modeling landscape here in an accuracy versus scale. We have tools that have very high accuracy, but low scalability because of, as I was mentioning, if you have traditionally, like in Python packages that aren't necessarily the fastest ones, or you have tools that scale and are built for packs, but they usually make assumptions about, I mean, they use simplified models to do the scaling, essentially. So they are using usually equivalent circuit model. So they're based on equivalent circuits. And what we're trying to do with JuliaSim batteries is to bring these two together so you can have an accurate tool that can also scale at large battery packs. Okay. So as one of the main application for these kinds of tools, electric vehicles need very precise modeling for the batteries that they run on. So you need to be able to predict the demands on the battery in a very short time, and also with a very small error. It's also especially important to be able to monitor critical safety metrics, of course, such as the temperature. You don't want your battery to overheat. If you're fast charging an electric vehicle, you want to be able to monitor the temperature and be very sure that it's not going to overheat, and you want to look at how the fast charging will affect the degradation of the battery, what happens during use. And now, speaking of this, in the process of designing batteries, it's useful to study different chemical compositions that you might use for the battery. And in this case, I'm presenting a comparison between several chemistries. So in the first plot, we have 1C charge. So we have this constant current, constant voltage protocol, and we have the same protocol, but we have different chemistries, and we're looking at the state of health of the battery. So it starts from 100%, and when it reaches 80%, we consider that as the end of life for the battery. And we want to compare several chemistries in order to evaluate what would work best for a given application. And this is something that can be used to inform design decisions around what can be used, what are the costs associated with several chemistries, what would be the expected outcome of using a certain chemistry in a battery, and also how does this change with the charging and discharging behavior. And one obvious thing that we can see here is that if you charge the battery faster, it's going to also reduce its lifetime faster. Okay. So why do this degradation process appears? And I was mentioning earlier the cell-to-cell variation. So one of the reasons for this is that you have manufacturing defects in the process of manufacturing the cells. So we need to also study the impact of manufacturing defects on the lifetime of the battery, on the battery pack itself, and ultimately how does this impact the performance of an electric vehicle in which these batteries are actually used. So this plot here is showing the state of health with the cycle number again, and the bands here are showing the variation that happens due to a manufacturing defect. So this is done by, so we know from the manufacturer that there might be a small error on like the thickness of an element of the battery. So they can provide us that, okay, you have a 1% tolerance for this parameter, and we have like 0.1 tolerance for another one, or 2% tolerance depending on the manufacturer characteristics. we can then plug this information in JuliaSim batteries, and we will estimate the remaining lifetime of the battery based on this information. And this here can also work with more complex charge-discharge protocols. I'm going to show a demo of this a bit later. Okay, so now let's go to battery pack analysis. So as I was saying, the aim for JuliaSim batteries is to bring accurate electrochemical models to the pack level so that you can also scale these very precise models to large battery packs. And here the technology that enables us to do this is a JuliaSim compiler. And here we have a comparison between the standard compiler, so the standard modeling toolkit, and the JuliaSim compiler. So JuliaSim batteries is implemented in modeling toolkit, and with JuliaSim compiler you can switch the compiler that is used to generate the actual Julia code that will run, or the actual code in the case of JuliaSim compiler. And this analysis showed that the problem is that I was saying in the beginning we have 300 DAEs for one cell. So when you have a pack which has 1,000 of those cells or more, then just the compile time of all of these equations will be prohibitive, and the runtime might not even be measurable in some cases. With standard MTK, this is a challenge because we have just the symbolic structure of the symbolic representation of MTK is not able to handle such a large number of equations. So in the previous talk, it was mentioned that you have very complex equations, and you end up after simplification with a few of them. Here, it's the case where we have a very large number of equations, and with JuliaSim compiler, we are able to take advantage of the repeated structure. So one of the optimizations that enables this scaling is we are taking advantage of repeated components. So here, another thing that I want to present before the demo is a fast charging analysis. So here at the pack level, we want to look at how does fast charging impact the degradation and the health of the battery depending on how fast are we charging the battery. And here we have each band is one charging protocol. So we have 1C, 2C, 3C, and so on. And one interesting thing to observe here is that the distribution of the cells in a pack varies with how fast are we charging. So we can see that for slower charging, we have a quite wide distribution. So 1% of the cells reach end of life by cycle 826, and most of them, so 50% of them, sorry, reach that by almost 900, so 899. If we look at the faster charging cycles, there we have a much sharper distribution. So with JuliaSim batteries, we can try to answer these questions. So because we actually model everything that happens, so we model at the electrochemical level what happens inside the battery, we can analyze this cell-to-cell variation and look at the cause behind this variation that we observe. And here we are looking at, in the first plot is the charging at 1C. It's cycle 899, so this is the cycle number where 50% of the batteries reach end of life. And we see that we have the CC region here where we have one charge for 2,800 seconds. And in this region, the red lines represent the cells that are below average, so that they're already under the 80% mark of battery health. And because they have been charged more, they have degraded faster, so this has impacted them more. And the ones with blue are the ones that haven't been charged so fast, and thus they have longer lifespan left. And we can see that if we compare 1C with 3C, the length of this interval here and here is significantly different. And this essentially is what would account for the difference in the distribution that we see for the cell-to-cell variation. So now I'm going to go to JuliaSim batteries. So this is an app that you find on Julia Hub. So it's right here. And it's available on Julia Hub. And after you launch it, so this is the interface where you can look at the battery configuration. So you can choose the battery model, you can choose the chemistry preset. So this is the chemistries that I was saying that we support. We can add number of cells in series, in parallel, and we also have sub-modules for things like thermal dynamics. And after that, we have the experiment. So this is the charge protocol that we are using. And we can just run an analysis and see the results for this particular charge protocol that we have here. And just a sec. Also, in these options here, we have also defect simulation. So what does this mean is that for some of the parameters, we can include a distribution. So it's not just one single value in the parameters for the differential equations that we're solving. We have a distribution, and we run the simulation here. We have like 100 times over, but you can repeat it even more if you want. And
now you use some standard geometry
yeah.
design?
Yeah. So here, if you look at the advanced option, so this is shows even more detail on how does the configuration and all of the parameters. We can go in even more detail here and edit everything if as needed. Okay, just gonna quickly refresh it. I think that okay. So we're going to import. So you can easily import configurations, okay, and run. Okay. And if you want to cycle, you can also, so a more complex charge protocol is represented here. We repeat it a number of times. So this is, yeah, this is what I wanted to show. So we can look at several characteristics like power, state of charge, state of health. And we can see here at the first cycle, the state of health is 1. If you go more advanced, then it went under 1. So that would be the end of the demo, so that I can leave some time for questions. With questions or without questions? Oh, okay, thanks. I thought it was with questions. Okay, so as I was saying, here I have a more complicated charge and discharge protocol that is repeated several times, so that we can also look at what happens with varying the number of cycles and taking a look at what I was explaining earlier about the degradation and how does cycling the battery over and over impact the battery. Now, moving on. Okay, we can also do an analysis on if we have batteries that we received from manufacturer in several batches. We might want to see the impact of manufacturing defects. So we might have things that are off spec or have a very high defect variance. So the manufacturer might, depending on the characteristics of the batches, we can take a look at this and do more complex analysis in order to analyze the impact of the defects on the performance of the battery and the resulting things in which is integrated like an electric vehicle. This is then can be very useful in analyzing which defects are the most important ones in order to improve quality control so that we know what defects we should target in the design process of the battery. And as I was mentioning, JuliaSim batteries is built on top of modeling toolkit and is also integrated with the entire JuliaSim suite so that you can do also all of the SciML. There's a lot of SciML talks here, so we have things like surrogate modeling. So you can take the model that you have for a particular battery, and if you want to accelerate that and just run that very fast and do optimization on that, or include that in processes that need to do quick estimations, you can use surrogate modeling. Or if you want to discover missing physics in the battery models, you can try to leverage the neural networks capabilities that are, so you can embed the neural network in the model, and this is work in progress into how to leverage the data that you have in order to discover missing physics in the model that fits the particular station that you have. So you might have a very custom battery model that you need, so your specific chemistry, you have data that you have acquired for the particular battery system that you are working on, and then that can be calibrated, and if that's not enough, we can go even deeper into scientific machine learning workflows and improve the models even more. So yeah, I think that's all. Thanks.
Thank the speaker. Do we have questions from the audience?
So I guess I have two questions. The first would be if you could elaborate maybe a bit what happens inside the JuliaSim compiler, what makes that much faster, and
yeah. Okay, so I think there might. I'm not sure if there is a talk on this, but the main thing here is that battery packs have a very repeated structure. So you have cells that are in series or in parallel, and they are connected, and we have the same structure that's all over, that's repeated. And instead of generating code that has all of the equations one after the other, and you have a very large chunk of equations that it is gonna be very slow to compile because you'll have to go through hundreds of thousands of them. You can leverage the repeated structure and have a for loop, and that for loop then can be can be vectorized. You can run that essentially in parallel, and vectorization at the instruction level. So it can be you can have very efficient code generation for that. And JuliaSim compiler also has a custom LLVM code generator, so we generate directly LLVM, and this can be, I mean, there are several things that help it reach this scaling, but those would be the important factors.
Okay, thank you. And the second question is, I worked with Modelica before, and I saw how people model battery packs with Modelica, and of certain interest was always like the interaction with the thermal system, because that affects the lifetime of batteries. I wonder what the advantage of using the modeling toolkit compared to Modelica is, because I think here it's more difficult to integrate this system with thermal systems, for example.
So with FMUs, or what you're mentioning? What kind of systems? I didn't understand.
Thermal systems, so the cooling systems.
Oh, thermal system. Yeah, so here the model itself has you can enable thermal modeling inside the. So here there was a. So we have thermal dynamics. So you can. So the thermal dynamics part is part of JuliaSim batteries. So this is part of the model inside the JuliaSim battery. So it's kind of already embedded in there. And we are working on expanding that, but yeah. I'm not sure if that answers your question.
Yeah, and then the advantage of using JuliaSim batteries in comparison to Modelica.
So on that side, so with JuliaSim batteries being implemented in Julia, you have the full power of a programming language. It's not just a declarative language, and this can enable more advanced things. The way that you are building a model is you can leverage things like for loops. You can build things that you have programming language constructs that are much more powerful than a declarative language. Of course, there are trade-offs. So some things might be easier to do in a declarative language, and some things might be easier to do in an imperative language. So this is a trade-off right here. And modeling toolkit essentially shows itself as a declarative language, similar to Modelica, but it's implemented in Julia. So you have both of them at the same time.
Okay, thank you.
Hi, thank you. You mentioned it sits within modeling toolkit. Can you combine like models of things like a vehicle inverter? You talked about the road test, and I can understand how they work together.
So the idea of using modeling toolkit is that we want to have a common base in which all models talk, so that you can combine a different model that is from a different part of the entire vehicle or the system with connectors, so that you have standard connectors that you can use, like if you have mechanical or electrical or heat ports and so on. So everything speaks the same language at the fundamental level, and then you can use this to integrate systems. Basically, the idea would be to be able to take, like, I don't know, you have an HVAC system and the battery system. You want to look at how does running the HVAC in your car impact battery life and stuff like that. And using modeling toolkit as the groundwork for this is what would enable us to communicate between models from different teams, essentially, because each team has its own model, its own experts that build a very good model for a particular part, but then everyone has to integrate together, to talk together, and we're leveraging modeling toolkit for this.
Okay, thank you.
So let's thank the speaker again with a round of applause.
Okay, sweet. Thank you. Oh, off for now, yeah. Thanks. Oh, yeah, I see, okay. Okay, perfect. No. Right. Thank you.
I'm gonna go see Chris, get Chrising. Are you going to give all array of Julia core talks this afternoon, memory and public and things like that? Next week? I don't know.
I mean, it might be. We can look at the events that they got going on.
Hi, everybody. So I guess we're going to get started here since it's past the lunch break now. My name is Thomas Baker, and I'm here today with two members of my group, Aaron Dayton and Kiana Gallagher. We're going to talk today about some software research that we use in the group, which we've been getting more and more emails about. So it seemed time to put together the final version 1 release of this. So I'll start. And what we're going to talk today about are some basic features of the library and some of the algorithmic perspectives that we have in the context of how we design this from just the base Julia library. Everything that you're going to see here today is only Julia, 100% Julia, in fact. And so hopefully this is a conversation starter with people here about design principles and things like that. So DMR Julia is a software package to model quantum physics. Basically at the level of strongly correlated phenomena. So it has a kind of a long history. I started this back in 2016, and then through a series of positions, which I'm grateful for the funding for, I was able to put together something that really reached the goals of Julia and being something that is simple, lightweight, and fast, and that also is as fast as lower level implementations of the same algorithms, although that was not the most straightforward thing. So one of the primary methods in this field is called the density matrix renormalization group. And what we do is we separate some big vector that is generally exponentially sized into a site-by-site decomposition in the basis of entanglement. Turns out that this is a good ansatz because physically relevant systems have what are called a local interaction, which means that you can essentially perform this decomposition and then you get a much more favorable scaling for the problem without losing too much accuracy. So there's this diagrammatic notation, which is to say that we can envision the large vector that we have as being some sort of tensor. And when we perform the decomposition, then we get a set of tensors that are represented on the bottom, and each of the legs is signifies one of the indices on the tensor. So a tensor of rank 2 is shown on the left with 2 indices coming off of it. And the entire idea behind the physics of this, and if you're not familiar, there's 2 references here, one of them in French and one of them in English. If you want to perform some sort of decomposition on a wave function in quantum mechanics, then you can perform this operation and realize that the decomposition in the space of density matrices is just the singular value decomposition. And that means that you're able to convert all of your operations down to matrix operations. So there's a very nice feature of Julia that it already has BLAS implementations of matrix operations, so we just leverage those in order to get ground state properties out of the system. If you pay attention in the back half of a physics curriculum, then you start to deal with things like density matrices and like entanglement. And if you know a little bit about the structure of quantum physics problems, you realize that density matrices, in terms of their natural orbitals, or the diagonal basis, the occupational weights of the density matrix will drop off very quickly. And so what this means is that any student that is entering this area typically will only get to this information in the later years of their undergrad, and maybe not ever. It involves a lot of computation. It involves a lot of things that you don't get to encounter until very late going. And then when you do see them in the context of thermodynamics or quantum mechanics, it's typically not emphasized in the same way that would make it useful in order to start working in a research group, which means that having code that is very easy to use, that students can have a very quick uptake time, and that they can essentially jump into research means that it's the difference between being productive in a research environment and not being productive in a research environment. So Julia was a very natural choice for this. During one of my postdocs, I had the supervisor went to another university, and I was left with 6 students who had to do this, and it became very quickly very obvious that existing software packages that I'd worked on and that were out there, and existing reference literature was not sufficient to train students up to where they need to be in order to do this. So that might have just been because of the institutional program that was there. It wasn't sort of geared into this area, and that's fine. Maybe that's happening to someone out there. But the tools that have been developed here, the students have a much more rapid entry into the field on the time order of a couple of weeks in order to figure out what's going on. So it's been very beneficial, and now that I'm getting more emails from people out there that are apparently taking interest in this, I thought it was a good time to kind of go public with it. So let's talk a little bit about how you set up some of the basic tensor network constructs in the library. One of them that is the most basic one is called the matrix product state. It's modeled off the Aflac-Kennedy Lieb-Tasaki state. And it's very good at capturing systems that have very short range entanglement. In the library, we have a very straightforward setup. So you can see that to actually start to run an algorithm, you'll maybe only need 7 lines of code. And if you want to run something that imposes quantum number symmetries, which can add a level of sparsity to the tensor networks, then this is only another couple of lines in order to do this. So very easy to kind of take something that's in the literature and then point to functions that are in the library, and then actually have the student just sort of say, go sentence by sentence of some algorithm that is going on in the literature, and then program everything that goes through. Now, if that's the wave function in quantum mechanics, you also have an operator. So here's a side-by-side decomposition of a matrix product of an operator, which is called a matrix product operator. Not as fancy as the matrix product state. And we have a nice auto MPO feature, which has been known in the community for a while, but it essentially allows you to write Hamiltonians as though you would be reading them in a paper. You can also extend this to 2-dimensional matrix product operators. So if you wanted to run a square lattice with arbitrary connections, then it would be able to construct the MPO for you. Obviously, the wave function ansatzes that we use here are much better for things that have smaller range interactions. But nonetheless, you can also extend this to quantum chemistry, and then you just get the same sort of structure here for a quantum chemistry Hamiltonian with a 1 and a 2 body interaction. The point is that you can just read something in a paper and then implement it in the code right away. We've also extended, and this is coming in the pending version 1 release of the library, to the 2-dimensional generalization of this. And this will work for any graph. You just need to supply the correct near neighbor table. But as you can see, to actually optimize this structure, in a lot of codes, they really bend over backwards to really make it efficient, I would say, and to get everything. We have it to a point where we have very little overhead on the actual optimization, and you can see that it's only a couple of lines. So a lot of the old literature in this field was written with a different purpose than educating new students, which is fine. It was really good work, and it really opened up a lot of possibilities. But having some code that actually makes everything compact like this is very beneficial for a research group. There's also this other graph ansatz called the multi-scale entanglement renormalization ansatz, and you can see our code is very, very short here. I haven't kept up with what other libraries are doing, but to do this in 12 lines is rather good. And it uses some concepts from graph theory that make this much easier in order to implement and to get people going on actually computing with these things. And I should mention that it's not just binary Mera that can be implemented here. That function to make the Mera net will handle any Mera graph that is in the literature. So it's quite a general function, and a lot of thought has gone into exactly how to design these things so that it's very general. We also have a variety of classical tensor networks that are implemented in the library. I think everybody knows about TRG that's in the field. That's the one on the left. It's just some decimation of a square lattice, although it can be extended to a Kagame lattice and a hexagonal lattice and a triangular lattice and a probably missing one. And then there's also the tensor network renormalization, which is another algorithm that is kind of using disentanglers to sparsify the problem in a slightly different way. All of these things are very small code bases. The student that is not here today, he was able to do this over the course of a couple of months, but basically implement an entire library of these classical tensor network algorithms into the library. And so we're hoping that this will be at least some sort of benchmark for future algorithms that may be made in this field. In order to download DMR Julia, it's a very simple procedure. The GIF that we have here is not sped up or slowed down. It's we're just typing very slowly. But it's 100% Julia, which means that it downloads very, very quickly. So there's no dependencies on anything. In the version 1, we are making a last-minute decision coming up here soon as to whether we include the OpenCL. So there will be some tiny amount of additional code that is there, but it downloads in a snap. You can start running it very easily, and it's as fast as lower level implementation. So we sort of achieved the Julia ideal here. So in terms of a few design points, this code has existed through several versions of the Julia language so far, and we're just waiting for version 1.11 to release version 1 formally, because we like some of the features that are coming out. But this essentially rewrites many of the Julia functions, so that 10 pack or the tensor pack that we were showing on a couple of the slides, that's essentially a replacement of linear algebra, because you need to have a slightly better way to access the tensor objects without introducing a type instability into it. And the thing that I have found that has worked, and if somebody has a better way to do this, this would be great, because then I could just use the base library a little bit more, was just to avoid the garbage collector, and that's largely the reason why everything is so fast. If anybody has any experience on GPUs, the status of parallelization in Julia at this point, some of the linear algebra functions and maybe the garbage collector, and I'll add one from this morning. If anyone has any experience on the RISC-V implementation of Julia, this would be a real treat to have some conversation with people about this. So in the next part of the talk, the two students that are in my group are going to take it and talk about some kind of externally facing features that are going to come out in this new functionality called DMR Genie that we're going to do. So go ahead.
Okay. So hi everyone, I'm Aaron.
And I'm Kiana.
And we're here to talk about a offshoot of Dr. Baker's project called DMR Genie. It is a website that will be releasing soon to allow users to very easily use some of these functions even without much coding knowledge. Mostly all built in Julia in the back end, and then, obviously JavaScript on the front end. But so there we are. So the back end is built using Dr. Baker's packages with Genie as the model view controller framework. So it all sits on top of that. Very easily, it was very easy to get it up and running. Genie is a blessing for this.
And on the front end, we use JavaScript with React. And the reason we chose React is because you're not really changing pages, you're kind of changing components of when you create these tensor networks. So we found it to be more efficient. And with React, we use the package React Flow. And the reason we use that is React Flow was actually built for like the typical graphs you find in computer science, where you have nodes and edges. And the diagrams for those are quite similar to tensor networks. So we chose to use React Flow for that reason.
So the app has two main components. First of all, an algorithm runner, and then second of all, a tensor network builder to allow users a wide variety of uses. So with the algorithm runner, currently you can run a algorithm called DMRG, Density Matrix Renormalization Group, which is one of the fundamental quantum algorithms for classical computers. It's broke ground, I think, around 30 years ago, and it still is very widely used today. With the full release of DMR Julia, we will be implementing some of the algorithms which Dr. Baker talked about, such as TRG, PEPS, and MERA. And you can also input custom Hamiltonians. So any physical system that you can find in a paper, you can just plug right into this website very easily.
And for the other component we have is the tensor network builder. And the idea is you can build tensor networks, you can run computations on these tensor networks that you've built, and using the output from this, you can use it with the rest of the library, like DMR Julia and 10pack.
So more on the algorithm runner. For this side, here is an example page of it. You have a number of sites. So here we have 8 sites. So that would be, say, 8 electrons in a spin model, and then you would apply some Hamiltonian, your model. Here we have the Heisenberg model selected. You can choose to compute certain correlation functions. You can choose to impose symmetries. It's just basically what this boils down to is there's some simple inputs, and it gives you a simple set of outputs. All of this is done with Julia Genie, where it just feeds the information through to the back end, and it just makes it very easy and efficient. So to run DMRG, you can do this to obtain energies, correlation functions, and then you can also impose quantum symmetries on the problem, and that gives you a whole other set of energies and correlation functions for that altered version. So currently, with this implementation. You can run on some known models from the literature, such as Heisenberg, Hubbard, and TJ, all things with known solutions and which give values you can check against. Then you can also input custom Hamiltonians, as mentioned earlier. So these are just very complex mathematical forms, but basically the entire idea is it would not be fun to figure out how to do this and actually code it up on your own. So this, you just see what it is in a paper, input it on a menu, you have constants, you have, you know, each operator, every single one you need is there, and then the backend connects with DMR Julia, does all the operations, and then gives you whatever observables you wanted, such as an energy or something. Then here's another example, just 6 components, the same for the Heisenberg model, looks a bit more complicated, but it's all very easy. You just copy what's on the screen or in the equation, and then it's as easy as that, really. It gives you the exact numbers you want. So.
And so we're coming back to the tensor network builder. And so, as I mentioned before, you can build tensor networks, you can run your own algorithms. It's nice to visualize tensor networks because sometimes when you see it in the code, it's really difficult to figure out, like, what does this actually look like? What am I doing? But here you can see it visually. And for that reason, you actually don't really need any coding background because as you can see, you can drag and drop tensors and connect them, and it'll do it all for you in the back end. And so the output, so what happens is once you're done all your computations, you simply click run network steps, and it'll do all the computations you've done up until that point, and then the output will be the tensors that resulted from the very last computation you did. And so these tensors, you're able to use them with the rest of the library if you need to continue the operations further. Oh. Huh? Oh. Sorry about that. So the operations that you can do include contract, singular value decomposition, QR decomposition, LQ decomposition, and eigenvalue decomposition. And as you can see on the GIF over here, it is doing an eigenvalue decomposition. So currently it is around 2 a.m. in Victoria. So we were unable to have the website public for everyone to use because if it were to crash, if too many people were to try to use it, we don't have any support that's readily available. But when we do release it public, it'll be done using the Digital Research Alliance of Canada resources.
So just to wrap up in summary, so in order to just to wrap up in summary, these are the download instructions, very simple. We're currently beta testing the version 1.0. Once Julia 1.11 comes out, then we'll be releasing that. And we have the DMR Genie slated for release very soon. So if we just want to say a bit of thanks for the people that are helping us to integrate this into the Digital Research Alliance of Canada, and of course the funding resources, and our beta testers that are making sure that there aren't going to be any problems down the line. So if you have any questions, we'd be happy to take them. Thank you very much for your attention.
Hi, well, thank you for the talk, and also thank you for fitting it in the 20 minutes, so we have plenty of time for questions. I really liked the interface. I think I almost couldn't tell it was Julia, which is maybe great, and then plus the graphical Genie interface was fantastic. But I'm kind of curious, like, under the hood, I can see you're probably using a lot of types to override BLAST operations, and it sounded like you have some custom implementations for tensors and whatnot.
Sure.
Can you talk a little bit about what's going on under the hood?
Yeah, sure. And then maybe I'll hand it off to Aaron and Kiana because they really did the front end. So on the back end, on the underneath side of DMR Julia, it's actually not even using the array type, which is in the base version of the Julia library. You can use the array type if you want to, but at least as a couple of versions ago, and then I never bothered to check because I've essentially, it's almost a very nice branch of Julia that has done some things that are very different on the back end. Right now, at this particular moment, there's a custom struct called a tens type, and it essentially just stores a vector, which we want to replace with the memory incoming, and then something to tell you what the size is. What this prevents, and this just felt like an easier way to program it, is that you're not constantly changing the rank of the tensor. And I felt like this was just something to kind of avoid, and it turned out to be rather quick in order to do this. In terms of what's going on the underneath side, essentially, and I regret that I had to do this in order to make it this fast, but a lot of the functions that you would apply onto the tensor have been completely rewritten. So I think one of the notable ones, and this is a very tiny one, so it's not something to get into a fight about, but the permute dimensions operation in DMR Julia is a little bit faster on average over all the possible permutations in the test that we have in the library, the unit test. So it actually derives some computational benefit to sort of go in and redo everything. I don't know what the status of that array type is at this point. I don't know. I know that there's some other groups that try and look at how to reshape these things and not have a type instability. But yeah, it's almost a complete rewrite of Julia, unfortunately. I wish we could have used some of the things, but we just wanted to avoid the garbage collector at all costs, essentially. That was the... But maybe you can talk a little bit about the back end of what you used for the front end, just to say a little bit about that, because it is. I agree, it is rather impressive what they put together.
Sorry, what was it in terms of the back end that you wanted to know?
I think your interface is fantastic, and so I just maybe wanted to understand a little bit more what's happening under the hood to make this work.
Yeah, of course. So basically, we use Genie. We built an app. It's just one line to do that with Genie, which makes it very simple. Then we use the model view controller framework. So if you used Ruby on Rails, it's very similar to that. You create some view in HTML, and then you add a route for that. So all the basic things. And that boils down to something that's very nice, I found, is that you can have Julia on the back end in routes or a controller, and you can have a .jl.html file, which allows you to call Julia in HTML and make it very easy. You can just pass variables back and forth. Any data is just streamlined to go from one end to the other, and you really don't have to think at all about what you're doing at that point. It's just very basic, and we couldn't find any alternatives besides Genie that actually allowed you to do that. Then for the JavaScript side, it's a little more complicated. We had to use some JSON and send it back because that's just what we found worked best with React. But yeah, I would say that about sums that up.
Great. Thank you. Did anyone have any other questions?
Apologize for being late, so I might have missed this, but do you guys benchmark DMR Julia against any other packages, maybe even other languages?
Yeah, I used to, just to make sure that I was sort of getting to the point where it was in the realm of being as fast. In scientific computing, as I'm probably sure that some of you at least are aware, there's very notable cases where people get really animated about these things, so I stopped doing that at some point. The story that I can tell is that in the quantum chemistry community, the very first quantum chemistry software that got really big was Gaussian, and that was made by this Nobel Prize winner, John Poppel. And then at some point, Poppel decided he didn't really want to do this anymore, so he handed it off to a student, and there's a very well-known group of people that have tried to compare their codes against Gaussian, and you get banned from having a Gaussian license. And John Poppel got banned from Gaussian. So there was at one point a website of people who had been banned from Gaussian. And I used to work on another tensor network library code and wrote documentation and developed things for it. And I just thought, it's, I figured any trick that anybody's playing, it's just going to seep into one code over another. I just wanted to concentrate on the design choices. The last time that I benchmarked it against the codes that I know of and know how to use, it was faster, but who knows, it could have been optimized to some other point. I think the other thing is that those low bond dimension scalings that you often find that people compare against, they don't really matter. Typically the BLAS routines take over. So long as you don't have something going wrong in your Julia code where you have a bunch of allocations, everything's going to scale asymptotically to the same point. So no, out of a courtesy, feel free to compare against. And if you find something that's inefficient, please send a request or get in touch. We're more than, we have no ego. We just want to do good science. This library has a lot of uses in the group. It's a group of 9, so there's a lot of projects going on. And these guys are just the 2 lucky undergrads who pulled this project. So, yeah, but if there's any thing that anyone notices, we always invite. I'm getting more and more emails about this, so it is useful if you want to take a look or something like this. Yeah.
Cool, thank you.
Anyone else?
Thank you very much. So you also use this for teaching, you said?
Yeah, I just ran a directed studies class because there's not really any other way for these students to access this. The papers that are out there are pretty pedagogical. They go in step. I don't know. There's like an infamous review of modern physics by Uli Scholach from 2005, and then a follow-up in 2009. These are great papers if you know what reshape is, but typically students coming in do not have this vocabulary, and so everything that's trying to be done here is to get the student to start doing research faster and not leave them kind of hanging. I think at least the groups that I came up in, we were never given code. You had to make everything yourself, which was, or the code was so inscrutable that it wasn't worth trying. And this is kind of like the one of the papers for the DMRG that was sort of just, I wrote it in the pandemic, and it probably needs to be submitted at some point finally, but it's called Build Your Own Tensor Network Library, because it's just like, why not? Why not know how to do the stuff that's going on inside of there? So, yeah.
Yeah, great, thank you.
Yeah, I can see why you would be interested in Julia 1.11 features, because there's a new memory basic type that array and whatnot are built on, and it sounded like what you were trying to do is a lot of maybe what static arrays does with kind of immutable vectors and array structures. So
yeah, exactly. That's why we wanted to just hold off on the version 1 release until we saw what was going on here. There's some other reasons that we're here. Like I mentioned, if anyone is interested in RISC-V, this is very much in our interest.
And you also mentioned OpenCL, so I was interested in what you were doing with OpenCL that you couldn't do with Julia.
Well, so OpenCL, this is one of the only times that I know when this has happened. The open source standard is just vanishing, which is a very strange concept. I think that just speaks to where NVIDIA is in the market right now. I used to do all the GPU programming in this OpenCL.jl package. And then it didn't work for a long time. And then now it's back, and the line on it is, we're looking for someone to maintain this, and I don't know if I want to do that, but definitely there's some possibilities to speed things up with a GPU in a tensor network context, and that's essentially what we want to do. Just regular matrix multiply and probably some other. I don't think there's a good SVD out there for GPUs that is general.
There's a library called I think kernel abstractions, which tries to generalize over different platforms, and it's not like it's in the right direction. I'm not sure if it's capable.
I used to play around with ArrayFire. I don't know if that's still popular now. Yeah. And like systematically something would break in these things. You'd go over the memory limit. You wouldn't know how to unlimit the memory. The other thing is it's so fast, partly because it's 100% Julia code on the bottom. So there's really, like, it really makes it very fast to download, fast to run, fast to maintain. I'm hesitant to introduce external packages into it at this point.
Right. Great, thank you. I'm moderating the next session. I'm Mark, so yeah, I didn't realize I was moderating this one too, but technically it appears that was the case. So. Hi. Yeah, it's nice to finally meet you.
Yes, nice to meet you.
So I'm just going to give a quick introduction and then turn it over to you guys. Jacob Quinn. organized this after seeing several Julia data mini symposiums put together that were rather successful. And I hesitated a little bit to put this together because I wasn't sure if scientific data was really that distinct from just data, right? But I think if we look at the data symposia, there's a huge emphasis on tables and kind of 2D data. And I think where I saw a gap was a need to kind of discuss n-dimensional data or high volumes of data, some data issues that aren't completely addressed by the prior symposiums on data frames and whatnot. And so, but I think given the interest in number of talks here, I think we seem to have quite the community. And especially these next 3 talks are going to be kind of highly related in terms of talking about data cubes and ZAR and a few other topics. So thank you for coming, and I guess we'll set up shortly here. Something I do want to kind of pose as a question both to the audience and to the speakers as they come up is really thinking about what makes scientific data different from data, and what kind of infrastructures do we need to build to bridge the gap between the strengths that we have in Julia data and expanding this into scientific data.
Okay, so just give me 1 second. Now we are already 4 minutes late.
Yeah, that's okay. So I'll just introduce your talk.
Yeah.
So the first of the talks is disk arrays at JL for working with large disk-based ND arrays.
Just open it from the website. Okay. Does someone know how to do real full screen? We don't need it.
And you have a microphone up there. And
Okay. Yes. So yeah, then thanks a lot for giving me the opportunity to. Does this work? I don't hear myself. So, can you hear me? Okay. Yeah. So thanks a lot, Mark, for giving me the opportunity to present this diskarrays.jl package, which is just to start with a quick overview what this package is for. It basically should help you working with data that is on disk and that is larger than fits into your memory, and can also help for working with remote data. It basically has 2 purposes. It can help people who wrap data formats into Julia packages for implementing the Julia abstract array interface for their data sets, and it can help downstream packages, like analysis packages, to have a unified interface to talk to data that might sit on a remote source or that might sit somewhere on your hard drive. And so as a very quick introductory example on why I think we need diskarrays.jl. So this is basically what we want to achieve. And here I take the netcdf.jl package, which implements this disk array interface, which uses it as an example. So we basically just open a data set. This is in a file on my local file system. I open a variable, and after that I can use this data object, which is an object defined by the netcdf library, as if it was a normal Julia array, and I can use like the Julia indexing, and what I get back is a normal Julia array, and then I do a plot. And in the end, we just indexing is just one part of the story. I mean, like if we want to have these arrays that live in some file format on disk, behave really like real Julia arrays, I mean, like indexing is one part, but then we might also just do some computation on it, do some broadcast, compute some statistics, do some reductions along dimensions, iterate over values. I mean, like, and usually that's really what abstract arrays are for. And I don't, since I didn't know which audience to expect, I hope I don't bore you too much. I just do a small reminder of the abstract array interface that is defined in Julia base. And as a quick walkthrough, I just put together an example here where we just define our own array type, and this is done, as you know, quite often in Julia. That when you want to have an array with some special behavior, you usually make it a subtype of this abstract array, which I do here, and I just put together the small example where we have an array that just wraps a normal Julia array, which is here this parent, and which just counts the number of times the array was accessed. I mean, so how often, I just want to count how often did someone read from this array. And all I need to implement here to get a lot of functionality is I implement a method for size, I implement a method for this index style to know if I want to have this array indexed in linear or Cartesian way, and then I implement a getIndex function. But I only need this one method. So I only need this getIndex that has as the first argument my array itself, and then as the second argument the linear index. And yeah, and here I define it in a way that it first increases the access count counter, and then just returns the value of the parent array. Okay. So then I can create my array. Here I make an access count array, and the first thing you see is that I already get a nice show method. So basically all of Julia's abstract array machinery generates me a nice representation of my array that it can be printed. And then I can see that my array, just after calling show, was already accessed 200 times, because show is doing a lot of stuff in the background to find a good representation. What else do I get for free? I get for free broadcasting. I can just add 3 to the whole array. I get reductions for free. I get matrix multiplication with some fallback. And you see that and that all this functionality is basically going through this one getIndex function that we have defined. And the Julia array machinery does this for me. We also have a lot of indexing. So getIndex is much more complicated than many of us know, and I also learned what is actually possible in Julia indexing when I try to do this for the disk arrays. So you have these funny things. I mean, like, so with Boolean indices, you can mix them with other types of indices. You can index with vectors of Cartesian index things, and so on. So all this is possible once you have an abstract array. And now what this all boils down to, or our problem that we have, is this assumption in the abstract array interface that the access to a single element is fast and doesn't have a lot of overhead. Because as you see, when we use this abstract array interface, it's doing a lot of calls into getIndex. And this is really something we need to avoid for an array that is stored on disk, or that basically lives somewhere in the web, because then we would have to do a request. I mean, like, so for every single access. And so we cannot, which would be the first impulse, just make our disk-based file a subtype of abstract array, because this completely destroys performance. I mean, like, you really cannot work with this file. I mean, like, I think everyone who has tried this, including me, the first thing is you wrap your disk-based array into an abstract array, and then you just hit enter. You want to look at it the first time, and then you see that show already takes 5 minutes to print a representation to the REPL for you, because it's just calling, doing so many C calls. So we have, for disk-based arrays, this significant call overhead, and we typically want to have an access pattern that we read larger portions of the file in a single call at the same time. And solutions to the problem. I mean, like, if you can work with mmap, that's great, and I think many people who do out-of-core things with large arrays use mmap successfully, but many of my arrays are compressed, are chunked, and so on, and so they don't really map to a single contiguous piece of memory, so that's not possible in all cases. One can do caching, but then you also have some overhead because for each get index call, you have some kind of dig lookup and so on. So I decided for the most difficult, but then also maybe most rewarding option to basically reinvent this abstract array interface that exists in base, but just based on accessing large chunks of the data. And here's an example for netcdfjl, how this is implemented, how we basically use this. This is an excerpt of the code that is in there. I just deleted some stuff that is not important. So basically, netcdfjl imports from disk arrays a few functions. Yeah, I mean, like this abstract disk array type, and our netcdf variable, the ncvar data type, subtypes this abstract disk array. That's the first thing we need to do. And then, similar to what we do for the abstract array, there we need to define a get index to access a single value from the array. And here, all we need to define is this read block function that comes from the disk arrays package. And this has the signature of, so the first argument is basically the array we want to read from, then the array, this is a normal Julia array, we want to write to, and this R is basically just a list of unit ranges that denotes the range in the array for each dimension we want to read. So for example, if this is a 3-dimensional array that sits on disk, the only thing I as a package author that I need to implement is for a 3-dimensional array, a method that given 3 unit ranges, for example, give me elements 1 to 10 along the first dimension, 2 to 20 along the second, and all along the third. Just this one method, I can be sure that I get exactly this number of ranges, and I implement this read block function in disk arrays, which is very similar to the abstract array interface, but here for reading blocks of data. And then, yeah, we just repeat this example. I made it for the access count array, and here I just make an access count disk array according to what we've just seen. So we implement size, we implement this read block for a list of ranges, and we create and we make an access count disk array, not just this access count array, but now we subtype abstract disk array. And then you see that similar to the array interface, we also get some behavior for free. So for example, we make this access count disk array, we get a show method. But in contrast to the abstract array, in this case, when we show the array, no data is read at all, because we want to avoid unnecessary lookups into array at any cost. Then, yes.
Maybe you're just coming to this.
Okay.
So now that you so now that you kind of invent your own interface,
Yes.
maybe this is actually the slide, but doesn't this mean that all the typical indexing and other nice things you can do that relies on the kind of Julia base interface doesn't work anymore because now it doesn't
Exactly.
have it has get block whatever?
I basically needed to re-implement all the base indexing methods in disk arrays.
Okay, but for example, if I call get index, I cannot
Yes.
do it on your data structure.
Oh, you can. I mean, this is what I'm doing here. So this is all get index calls.
And then it goes through get
And then
block.
it goes through the disk arrays. The disk arrays basically, what disk arrays JL is doing in this case, it's translating these get index calls not into single calls into the function, but basically into, it basically reads, in this case, it's reading a bounding box, like the outer bounding box of the data that you have accessed. It's only doing a single call into read block and returning the values that I actually
okay, thank you. Yeah.
expected. So this is basically what we do, and so we re-implemented. I would say most. I mean, because like base indexing is so complicating, but really a large part of the base indexing machinery is working like here in these examples, and because we only did 3 calls into get index, so, and in the end, our disk array only got accessed 3 times. But we didn't stop there. We also implemented an own broadcast style. So basically, we can do broadcasting, and here we said, okay, let's do broadcasting lazy by default. So because what we want to avoid at all cost is that you run out of memory. I mean, like, so we never read like the full set of data if the user does not really say that they want it. So basically here we have a lazy representation of the disk array plus 3, and only when we say copy, like you get the result, and then the data is also accessed only once. Like we have reductions, so there are overloads for reduce, map reduce, and which also sum falls back to, so that you can do a sum over a single dimension. You can also do reductions on these broadcasted disk arrays, and so on. So some simple operations work after we implement this abstract disk array interface. To summarize, so package authors implement read block and write block, similar to set index, get index for single elements, what you would do for normal abstract arrays, and in return you get indexing behavior like they are as it is in the abstract array interface, but while minimizing the number of calls. And currently, this disk arrays is backend for tar.jl, for netcdf.jl, to let's say 50% in NC dataset. It's not completely integrated there yet. It's in ArchGDAL for the arrays that you can read from there, encrypt datasets and HDF5 utils. Not yet HDF5JL, maybe in the future. I mean, there is an open issue, we can discuss this. And in addition to the indexing, you get lazy broadcasting and reductions. And I didn't talk a lot about this, but in the end here, the data is in a serial way. I mean, like in this simple fallback implementation that we have in disk arrays.jl, it's just serially accessed chunk by chunk so that you never run out of memory when you do your reductions. And so that I would say that's suitable for medium-sized out-of-core arrays, so like some 100 megabytes or something like this. So some things that doesn't fit into your memory. But when you want to do something huge, distributed, you would need to rely on other packages. And so that means other packages can be built on this disk arrays to provide this. What's the time? I just want to, okay, good. Yeah, and since I already said, okay, the data is accessed chunk by chunk, something that I didn't talk about yet is the data chunking. So most of data sets that you find out in the real world actually have, I mean, like HDF5 enables this, netcdf tar and so on. They have some internal chunking to optimize access along one or the other axis. So that means your data is basically not, your whole array is not stored like linearly in the array, but you define some internal chunking structure in which data is stored together. And since this is such a common theme, disk arrays.jl also provides some primitives to talk about these chunks. And going back to netcdf.jl, I'm like how it implemented this. Basically, when you want to, when you are the package author, I mean like that wraps some data format, you need to implement 2 methods. I mean like first is this has chunks. So where you basically say, is my data set chunked or is it not chunked? And the second one is an each chunk function, which then basically returns an iterator over all the chunks that my, like of the indices of the chunks that my data set has. And yeah, this, yeah, and okay, that's just the summary. So what happened in our former example, we didn't define hash chunks there, so then it defaults to unchunked, so which means it doesn't know the chunks. So whenever it's doing a reduction, it basically just splits the data set along the last dimensions so that it just fits in memory. And when it's doing its loops. So just as a small example, how packages, I mean, like how you can create these chunk types. I mean, like, so disk arrays, for example, provides this grid chunks object, which is then always making an outer product. So for every dimension, you define the chunks. I mean, like so as either regular or irregular chunks. I mean, like, depending on if they all have the same size or if they vary. And then you basically make an outer product of it, and then you can just loop through this grid chunks objects when you want to do something serially with every chunk, or you can even do it in a distributed way when you put a PMAP there. So I mean, like, that would be a nice way to work with, for example, when you have a ZAR data set or so. You can, when you are writing downstream code, I mean, like, when you want to work with this, you can, for every package that supports the disk array interface, you can open a data set, you can query the chunking structure with this disk arrays.each chunk. Here we have a very small netcdf file, so basically that's the whole data fits into one chunk. So that's not chunked, so basically this iterator just returns a single value. But for example, when I open a huge ZAR file from a remote source, I open it just from this URL, and then I call this disk arrays.each chunk. I basically get here a long iterator of the indices that I could loop over, and I can write code that accesses data in an optimal way. So the summary is that, okay, downstream packages can query the chunking structure of any data set through this each chunk function and optimize their data processing pipelines. And just as two examples, both from me, because I make, for me also the disk arrays is just a means, I mean, like, to wrap different data. I make so we have this YAX arrays package, which basically has easy parallel map slices like operations on large data sets. I mean, like, that can just work on any ZAR or netcdf or so, or a grep data set. And since 1 or 2 years, I'm doing basically a large rewrite because of this, and I'm writing on this disk array engine. It's currently more or less a prototype library for doing large parallel moving window operations over huge arrays, using Dagger and so on. But that's still work in progress. It's test registered versions. Some people use it, but I wouldn't recommend it for use yet. An alternative, and I think which is a very low-hanging fruit, because I once did an implementation of this, like in the morning of this, is when you talk about Dagger.jl also has this D-array data type, where basically it has an array separated into different chunks, and it's very easy to map basically the chunks of a Dagger D-array to the chunks that a disk array has on disk. And I think it would be very good to, there's an issue about this, and it would be very good to pick that up at one point anymore, if you're into Dagger and if you really know about what these the array types are doing. In order to still allow for a few questions, okay, I would skip this and summarize. We have this disk arrays JL package, and as I already said, it's good it's there for two use cases. When you are a package author, when you have wrapped some multi-dimensional package, consider using disk arrays to implement all the nice array stuff with just a few lines of code. And when you are writing your framework and you want to do some big data analysis on huge arrays, you might depend on the abstractions defined in disk arrays JL to get basically to have a lot of sources, data sources. I mean, you've seen the list of packages that implement it, and to basically write code across different data sources. And a big thank you to all contributors to disk arrays: Felix, Raphael, Alexander Barth, who's constantly pushing for some more special cases, and to everyone else who helped. So thank you.
Okay, do we have any questions? Otherwise, I'll lead with one. Quad first, and then.
Thank you. Thank you for the nice talk. Will this affect the speed of find? Let's say you have an array of strings, really big, it's in disk. Not just numerical, but when it comes to strings.
A string. You have a string. You have an array of strings.
Suppose you have an array of suppose you have a lot of mutations, and they have strings attached to them. And with this, you can probably put the entire chromosome in disk and then access it. But for each position, you also need to access some kind of string information about that. And it basically, I guess another question is, will there be a disk dictionary equivalent of disk array that goes with disk array that allows a very fast random access?
So I would say currently not. I mean, so the focus of this is really like on wrapping like the arrays themselves, multidimensional arrays. Yeah.
Thank you so much.
More or less.
Maybe one quick question: have you benchmarked against using memory map, like mmap, for like uncompressed normal data? Do you know how the performance kind of compares?
I have not benchmarked, but I'm almost sure that mmap must be faster. Yes, I mean, like, so that was not the goal. I mean, like, and I think you cannot reach the mmap performance because, like, the operating system can do more magic. I mean, like, of course, for you when you use mmap.
And so then you said you re-implement show because you say usually show takes get index many times and actually get index is still slow. So now it's fast to do get block, but if you call get index is still not so fast, if I understood correctly. So then I'm thinking if you have like a linear algebra algorithm, let's say a single value decomposition, which does need to do like there's no way around doing get index many times. How does that kind of work with your package?
No, I mean, like, so there is. Currently, we have implemented the things that work well, but of course, linear algebra, SVD, or matrix multiplication also, this is not in the scope.
I see. Yeah, thanks.
We're starting to see some two-level chunking schemes with maybe shards or blocks where you have larger files that then contain smaller number of chunks. Do you think we need a new interface for this, or can we fit this within disk arrays?
Okay. I'm like I only need I only know the shards from ZAR. I'm like so they implemented, and there it's a different concept. I mean, like, basically the shards are basically just not as important like performance-wise as the chunks are, because like the chunks are compression units and the ZAR is basically just in the shard is a storage unit, and so I personally don't see a reason yet to extend the interface, because that's really, to me, that's an implementation detail of the respective backend. And yeah. So currently I wouldn't see a need to talk about shards here.
Okay, thank you. Are there any other questions?
Yeah, I have one. I've been using disk arrays a bit for like a package I'm implementing, trying to. But my data is stored as like data records where we have like small arrays, and then the variables are stored in there. So the chunks of the variables are kind of mixed in together. Is disk array an okay solution to kind of handle this lazy loading of these variables when the chunks are mixed?
So the question is, if I understand, so it really depends on are the chunks mixed across like also across dimensions? I mean, like, so I'm not 100% sure.
So one dimension is in a trunk, and then the other dimensions is like different chunks.
Yeah. So this is not a problem.
Okay.
Yes. I mean, this should work. Yeah. Yes.
Thank you.
Okay. Well, I think there's no other questions. We'll move on to the next talk. I think we have a series of related talks after this, and so I think Felix and Fabian may be switching on and off, and finally Raphael will end the first sequence. We'll have a break and then continue the mini symposium after the break. Thank you, guys.
Okay, so I'm going to continue with actually usage of disk array engine. So I'm going to talk about pyramids and how to plot large raster data interactively. So what is a pyramid? So the idea is we have very large data that we can't fit into memory or on the screen, but then we can build a pyramid out of it. So we aggregate every 2 by 2 pixels together, and then the next level and the next level, going from high resolution to coarse resolution data and thereby decreasing the amount of data that we have. Then we want to compute these pyramids for our data. So there's basically currently 2 ways. You can either do it in memory, starting from any abstract dimensional data array, and then basically calling pyramid here and setting a resampling method. And then this takes some time. So for this raster data, which is 40,000 by 20,000 pixels, it takes around a minute. And then for larger data, we can also just do it on the disk. So we start from a data set that is already available as a ZAR file, and then we save the pyramid also into the ZAR, and saving the different levels as different subgroups. And this computation is currently using disk array engine. And then we can also access pyramided data. So there's also pyramid data in GeoTIFF, for example, or I think maybe also other TIFF types. There's pyramids in ZAR. So we can just load the data from a path or even from a cloud, from an S3 bucket. That's kind of working, but the latency currently is still too high that it's actually usable. And then after we've done all of these preparation steps, we can actually use this to plot our data interactively. So here we saw our data is 405,000 by 175,000 pixels. That would just crash the machine immediately. And so we see the different layers are getting smaller and smaller until we get somewhere that we can actually put on the screen. And to just do that, we can then just plot. This is above ground biomass data for the whole globe on a 100-meter resolution. And then we get the global picture, but we can also just interactively zoom into here. Or we can have a look at the Amazon, where we can then see some deforestation patterns. And that works quite interactively, quite nicely, because the plot is at all time only accessing the roughly 1,000 by 500 or so pixels that you actually need to put the data into your figure. And it's going to select the resolution based on the area of interest that you're currently looking at. But then we don't only want to do nice interactive visualizations, we also want to do computations on the data. So the next step is we get multiple of these pyramided data sets and do computations on them. So here we just do a broadcasted diff. So currently broadcast is implemented and map for a single pyramid is implemented, so that we don't only we do the computation not on the full resolution and then wait for a few hours to maybe a few days, depending on your data. But here we can just do this, get the lazy broadcast from disk arrays, and then immediately get this result. And then we can also just plot the result. Which should be, oh shit. And then you get immediately the whole globe on the coarsest resolution. So this is just a few thousand pixels per. But then you can just zoom in and say, okay, that looks interesting. Let's have a look at, okay, what is happening here, or do some do some other analysis that you, normally you have your area of interest that you're mostly looking at, that you like, oh, these are some areas that are sometimes working, sometimes not, so I want to first look there, and then I see whether it's okay-ish working, and then I can start the analysis for the whole full resolution data. Yeah, and that's basically the main aim of pyramid scheme. And so just as an outlook, so we also want to do pyramids in multiple dimensions, so not only space, but maybe also time, and also either just have the pyramid on every time step, or even do pyramids in the time dimension. So do aggregations on time. I'd like to also see more use cases, maybe for other fields that have also large data that are interesting to look at. So understanding more formats, integrate this all with the disk array engine computation, so that we not only do broadcast, but can do more interesting map slices, moving window operations, and yeah, thereby opening it up for more use cases. Thanks.
So currently you're mostly showing us 2D kind of pyramids, but could you do 3D right now? You said space, so.
Yeah, it's not, I mean, currently it's just, the pyramid is only computed in 2D.
Okay.
So I think that's basically the next step I'd be working on, to also get 3D, or actually, or the time dimension is more interesting for us, is like, but then also sometimes it's not clear, for me at least, not clear what the interface would look like. Because in 2D, everyone is basically nowadays used to zooming into a map.
Sure.
It's clear how to define your area of interest. But for time, there's also some interesting questions there.
I work with time data. What I wanted to ask, I don't know if you covered it and I just missed it, but when you're doing the pyramids, it's some sort of like aggregation, but can you choose the aggregation function, or is it always mean?
No, you can, here in your computation, you can here set a resampling method. That can be, basically it gets a 2x2, I mean, we could even think about doing other resampling or other aggregations, but currently it's just doing the 2x2 moving window, and basically it expects the 2x2 matrix, and then you can do whatever you want with it. So you can any Julia function, or even, I mean, yeah.
Thanks.
Okay, any further questions?
Hi, thanks very much. Do I understand this right, that this basically this raster which defines of how the hierarchy actually works, that this always has to be some kind of matrix? So could you, so basically like zooming in means that you're looking into like based on some kind of like a rectangle, so that you're basically zooming in through like a rectangle? Because I've only learned recently that Uber actually uses hexagons in order to have this hierarchical format. And so I'm wondering whether is that a smart idea, or is that actually just like fancy stuff that no one actually ever would use in practice? So basically just wondering whether do you have to stick to this like raster being like a rectangle, or can you zoom in with other shapes?
You could zoom into other shapes. I mean, the hexagons, this is more of a DGGS. I can't remember something dynamic discrete global grid systems. So the idea is to get rid of the problem that you have not equal area. For example, if you have that long rectangular pixels. A colleague of mine is currently working on a DGGS Julia package. And we are also discussing how we can link these together to get pyramids on, or use pyramid scheme to compute the pyramids for the hexagons in a smart way, and then also be able to plot them.
Raphael, if you want to get set up. Are there any further questions? Just quick question about your demo there. Was that data that was on your laptop, or were you loading it live? Okay.
That's demo. I mean, the doing it on. We tried it on the cloud, so it's should work, but the cache is. I mean, it works if your cloud is local enough. So we tried it when we had it on the server in the same network. Then it was smooth enough. I wouldn't want to rely on the network here, or I think we might want to get some proper caching or some other tricks to actually get it more snappy.
Right. I was curious, like, if you ever tried this in like S3 or so forth. Okay, you have.
It was working in our local network. Yeah, so we tried, and it was working in the local network, and we think we can make it work, but we would need some. I mean, we have already once talked to Simon Danish about some caching strategies. I mean, especially for the zooming and so on. And I think, yeah, it would still be a bit more work.
Okay. Well, thank you. So we're going to move on with Raphael. He's going to get into the dimensions part that we just alluded to. Raphael's coming from Copenhagen, and I think you have an ecology background, if I understand. So, thank you. Please.
Thanks, everyone. Yeah, this should follow on from disk arrays. Actually, dimensional data and disk arrays are often used together in most of the packages they're used in. And also, I think pyramid scheme is a dimensional array, right? Yeah, so they all kind of work together. So, first question, maybe people in new to Julia don't know about this, but there are a lot of dimensional array packages in Julia. I think there's like 7 if you count the edge cases. And so I'll just answer why this one exists, basically. I think it's justified itself now, but in the early days it hadn't. So the problem is geospatial data. Name dimensions and lookup values are ubiquitous. We have X and Y, latitude and longitude coordinates. We have time dimensions. And we use them to select spatial and temporal areas of our data all the time. But NetCDF, CF standards have a lot of complicated ways to do this. There are a lot of different kinds of lookups. They can be ordered, like aligned or unaligned with the dimensions. And also multi-array data sets are really common, where you have multiple arrays of different dimensionalities sharing some dimensions. And none of the existing packages could do this. This is something that Xarray can do. The name is cut off the bottom of the screen. But so some of the motivation was to have something like Xarray in Julia, but also something more abstract that we can use as a backend for a lot of the spatial packages. So I'm going to try and explain what it does. I'm not sure everyone really understands a lot of the concepts when they're using dimensional data, even though it's getting kind of widely used. So first, I'll talk about what a dimension even is to get started. So dimensions, it's just a wrapper type. It's a very dumb thing. It's one struct that wraps something else. And this act of wrapping something tells us what dimension we mean this thing is from or related to. And that can really be anything. It can be an integer, so we can see the first item on the X dimension. It can be a range. This may be the lookup along a dimension. It can be a selector. Here we're saying things on X not at 70. But really this can wrap anything. So it's kind of extensible to be used to relate actions to dimensions. We've defined a bunch of standard dimensions, X, Y, Z, and time, because we can't really use time or T. And this like, standardizes spatial data, but we also have just generic dimensions where you can name your dimensions anything you want. But they're all subtypes of dimension. The next concept is lookups. These used to be the same thing, and they're separate now. A lookup is an array that holds values along a dimension, has traits like points and intervals, but most of these are detected automatically from your data. So like when you're using dimensional data, half the time you don't know these exist. They're kind of in the background making things work. But they allow us to dispatch on some of the things I'll show you later on to give correct selecting behavior over intervals and points and fast lookups, so we know the order of arrays already, things like that. You can define them manually when you need, and here's a sampled lookup, the most common one, and it's a abstract sampled aligned lookup. So there's quite a family of different kinds of lookups. We have lookups that can take X and Y dimensions into account, so we can deal with the rotated and skewed lookups. But mostly you're just dealing with sampled in everyday data. Next, I'll show you the basic main use case is building a dim array or using a dim array. And a dim array is an abstract dim array, which is just an abstract array. So mostly it behaves just like an array, unless you use special indexing. This is the simplest way to make an array. We've made an array with a small vector of numbers and a dimension holding a vector of values that relate to those numbers. So you can see that those are detected as being categorical values. And so we have an X dimension of categorical values where A is 1, B is 2, C is 3. But you can expand this arbitrarily, largely. So we can make n-dimensional arrays. Here we have X and a Y dimension, a categorical and a sampled dimension. And actually this prints way nicer in the REPL now. It's all colored, but it doesn't show in the slides, unfortunately. We can also make arbitrarily named dimensions just by using a name tuple to define the array. And then we have dimensions called A and B. And people in stats and other fields like these more, but I think in spatial data we mostly use the X and Y. We can also do things like just run rand or fill or zeros using dimension wrappers and get a dim array back. So you can define as a shorthand to making a quick array that has named dimensions. We also have this thing called dim stack. I think people really don't know what this is. And it's less often used directly, but Rasters uses this for NetCDF, for HDF5, for any data sets that have multiple arrays sharing dimensions. And it lets us index into those and use them as if it's one array. I'll demonstrate that a little bit. So it's an abstract dim stack. And the point of these always being abstract type is everything works in the abstract type, so it's all extensible. And that's kind of why I think it's been used more, is because you can make your own types behave like this very easily. So we can define a dim stack using layers with the same dimensions. Here we just define a name tuple of arrays and then pass these X and time dimensions in. So we've got two arrays, layer 1 and layer 2, with the same dimensions here. But we can also use different dimensions. So we can have an object with mixed dimensionality that we can still index into that has, here we have 2 dimensions for one of the arrays and 1 dimension for the other array. And this is actually quite common in NetCDF, where you have layers that have X and Y spatial dimensions, and then you have another data set that has a time dimension as well. So you're kind of using them together. So this is the main thing dimensional data is for, is named indexing. And this is some benchmarks of that, just to show you this is a cost-free process. You can use this in inner loops. It's very fast. So you can see here I'm using 3 and 4 in Julia base array syntax. But I can use Y4, X3 out of order just to demonstrate that it works. It flips them around the right way. Or you can use this keyword syntax, Y equals 4. And there's no cost to that. It's free. It's a compiler action. And you can see also with dim stack we have the same. It's only 3 nanoseconds to get a name tuple back from a stack using these keywords. The next use is to use the lookup values that we have in spatial data instead of just the names of the arrays. We want to select data using our lookup values, and we have a bunch of things called selectors. The first is @. This is just the shortest word I could think of that meant this. I want to have a wrapper type, so it's different to standard Julia indexing. But we can make an array, and we can index into it with @. Here I'm going A X at 80. So I want the value on the x-axis at where the lookup value is 80. But I can also do it with x at 80 point something with a tolerance. So if you have data it's not quite exact, you can use that. There's also near, which just finds the closest match, similar to @, but contains. finds the interval that contains a value. So you can set up your axes to be intervals rather than points, and you can find which interval contains the value that you want. So it's like near but more accurate. And this will work across all different kinds of intervals, where you have irregular intervals, regular intervals, exactly specified intervals like you get in NetCDF. So yeah, there's a lot of dispatch in the back end to make this just always work the same way. We also have ... which is interval dot sets notation, so we can just select our range, 9.5 ... 15, and we'll get back all the values inside that range. We can also use these multi-dimensionally as well. I'm just showing one to be simple, but you can be indexing 4 dimensions at the same time like this, or less. You don't have to specify the dimensions you're not interested in. Last, we have where, which is like a dimensional query, so we can query values along a dimension. Here I'm saying I want all values of x where they are odd numbers, and you can see the result. We have 1, 3, 5, 7, 9. So you can use that as a way of probably you're not going to use is odd, but some other kind of spatial query. You can use any function you want in there. And that's a function of the lookup values. There are a bunch more selectors as well, but they're kind of similar to the ones we have, like touches, and no time to show them here. The next thing dimensional data does is plotting. So it allows any package that extends dimensional data to get free plots.jl plots and Mackie plots that should have the right labels and put the right labels in the right place. So arrays will be permuted and reversed and turned around so that everything's in order, and hopefully like X is on the X-axis, Y is on the Y-axis, things like that. So here we can make a scatter plot with plots, and we can just plots.scatter this random array, and you can see it's labeled A, B, C, D with the X label. We can do the same with Mackie. We can make a heat map just over a normal random dim array, and it's labeled with categories and values along the bottom. And last, I want to talk about the integrations. Dimensional data uses all abstract types everywhere, and that was intentional from the start. It was made to be built into rasters.jl, but I didn't want to put all of this code in a really geospatial package with a lot of dependencies. So you just need to write a dims and rebuild method, and other array types will work like a dimensional array. So broadcasting will work. All those things will maintain dimensions over time. And so far we have, there's probably a few more packages now, but rasters, Yax arrays, climate base, astro images, pyramid scheme, and then some modeling packages, RViz, jump, and dynamic grids all accept and use dimensional arrays and output them. And let's say thanks to all the contributors over the last few years. And also we can just check out the new docs. Lazaro remade the docs, and finally I think we have actually good docs. So there's a whole lot more detail than I could talk about today, but you can actually find out what it is now. They're quite nice. There's like walkthroughs of easy things, and then various things. We have group by and other cool functions like that I didn't have really time to talk to. Anyway, is that time?
Yeah, we're right at time, so there's actually a little bit of 5-minute buffer, so we have time for questions. And then right after this, we're heading into a break. There's a little bit more food downstairs if you missed it at lunch.
Okay. Thanks for the presentation. One question. So you mentioned there are a few packages that try to do similar, offer the similar functionality. One that comes to mind is data frames, because how different is data frames from the package that you're showing now? What are the main differences, and what are their use cases?
Well, data frames is tabular data, so they're all vectors. So every column is a vector. So the dim stacks is a little bit like a data frame in that you can have multiple columns, but each column is multidimensional. So everything it's aimed to be multidimensional. Okay. But you can convert you can convert a dim stack or a dim array directly to a data frame. So you get the dimensions as columns, and then the data as another column.
I see, I see.
And that will be lazy, so it won't actually use all the memory.
Yeah, thanks.
Yeah.
Hey, thanks a lot. Crazy efforts that you've put in there. How far do you think you are from, like, what's missing compared to X arrays? Yeah.
I don't know what's missing now. Probably like some of it, like dimensional data is not trying to do everything X array does, because X arrays is like everything but the kitchen sink kind of. X arrays has disk arrays and Dask and so much stuff. Where dimensional data is just a layer at the top, and those things like disk arrays can happen internally. You can put any kind of array inside a dim array. So the idea is that a lot of that functionality should be contained in the arrays that dimensional data arrays wrap. And Rastus does that, you'll see in the next talk. I'm not sure what else. What are we missing now? We recently, Lazaro got me to make group by and a few other things that were just like, we need this, we don't have it, but group by could be better. I don't know. Do you guys know what's missing?
Awesome. Thanks.
Yeah, 1.0. Any other questions?
Maybe a naive question. How feasible would it be to use this as a surface, whereas like the underlying array is actually unstructured, so that you could basically have data, let's say if you're thinking about data on the globe, in a completely unstructured way, and you still could say like, hey, I want to give me the data at like this point, and so suddenly things like near or at become like bit of like weird things, right? Because they're technically like you can't necessarily represent that as a matrix anymore. And so do you think there's like actually like it's feasible to completely hide the idea of unstructured data from the user, and so the user would just use it as if it was like nice like X, Y, Z, but actually it's basically everything is just a vector underneath because you can't represent it into any structured matrix form?
Yeah, if you can make some other abstract array type that works like that, then it will work inside dimensional data. But like it's really built around, like you have a multi-dimensional array. It can be a sparse array, right? But it's a multi-dimensional array, and the axes have to be the same size as the lookups. So there's no capability for handling anything except an array, basically. Yeah.
Okay, so we'll break for 10 minutes. We'll start back here at 9:40, again with Raphael on rasters.jl. So see you guys in 10 minutes.
Yeah, I'll come and get some. I'll just get set up for a minute. Yeah. Was that too much stuff in a talk?
I think you're fine. What are you going to talk about the rest of stuff?
All the other shit.
What other shit?
Food? You don't know. It has all the geospatial
Oh yeah,
tools.
I mean,
it's like the rasterization
yeah,
and stuff.
Oh yeah. Okay.
Masking, zonal statistics.
Next time, just copy paste my name and.
Ah, did I spell it wrong? Ah.
Oops.
Oops.
I have a naive question.
Are you doing this?
So I'm also used to ecology, but
Yeah.
using environmental DNA. So I'm
cool.
wondering if you have opinions on using Julia for temporal analysis, but whose resolution is not as good as the modern time series.
What kind of temporal analysis? Like models or spatial models or?
Right, so I'm working on this. I think the time points that we usually have for paleoecology is not as good to. I wouldn't call it like to fit, because usually
you need to do like time series analysis. There's a bunch of packages for time series analysis.
Yeah,
in
but
Julia.
I guess the question is, the problem is that we don't have regular spaced.
Okay. Yeah. There still should be packages that can handle that somehow. I don't actually know. I haven't done anything like that. But to me, you would only use Julia if, like, at this point, if there's better packages in Python than R, like, I would just use them. But if you have any performance considerations, if you have heaps of data or like complicated models you have to run a lot, that's why you would use Julia, because then it's like anything you're missing, you'll make up for. But if you have no performance problems, like it's hard to beat R and Python, except R's kind of a mess and hard to understand. Julia's very clean, but there's still functionality missing. Like I have to write, I'm just an ecologist, I have to write all this stuff myself.
I see. You mean
Right.
for your Julia packages?
Yeah, I have to write so much stuff just to do basic analysis.
Exactly. And the reason you use Julia is because of performance.
Yeah, because I do simulations. It's Julia or Fortran, and I'm not going to use Fortran.
How long
basically.
did it take you to start from knowing Julia to being able to write a full package?
I think 3 months.
Oh, that's good.
But
Okay.
I've been developing for 10 years before that, so
I
I've
see.
already programmed.
I see. So you were born as a developer, not an ecologist.
Yeah, I was a developer before an ecologist. Yeah, so that helps, right?
I see.
I didn't really realize I did science, I did geography, and then I was getting into ecology, and I didn't have all the prerequisites, and I went for a supervisor. I was like, oh, I don't think I have the biology. He's like, oh, that doesn't matter. The programming's the hard bit. Like,
I see. Yeah,
so
exactly.
so it's kind of programming is big in ecology now, so it helps. But
I see.
that wasn't the plan. But
I see.
yeah.
Okay, thank you.
So yeah. I'm gonna talk next as Raj. Where are you? What lab are you at?
In Germany.
Is there food out there? Or?
I don't know. Usually we start for.
Oh yeah, sure.
Alright, sounds good. Internal Julia server error. Wauw. Komt goed. Nee, maar iemand heeft een mailtje gehad.
blik waren er iets van 100 mensen die de e-mail gehad hadden. Nou, misschien voor mij niet meer nodig. Ik doe virologie, dus ja, wat wil je? Ik denk dat, ja, ik denk waarschijnlijk iets met API. Ja. Ja, prima. Maar goed, dat is toch een vaag nieuwtje. Het is niet behulpzaam. We kunnen nooit het niet echt spelen. Nee, maar ja, iedereen wil het tijd. Maar sommige krijgen dat natuurlijk helemaal niet doorgaan. Nee, hoe het in het algemeen wil, maar ik ben niet helder voor. Nee, het is net, maar het is gewoon bij mij van het begin af aan niet helder geweest en nog steeds niet helder. De wandelgang nu met de twee onderdelen, de onderhoud en de nieuwe worden samengevoegd. Ja. Dat staat niet letterlijk in de mail. Wat is er nog precies aangekomen? Het zou nu echt zijn. Totaal gescheiden. Wereldoorlog of dezelfde afdeling. Dezelfde plek, toch? Wat was het beter als je nog weer wat ik van begrijp is nog niet een andere onderwerp nemen. Of je fix of je doet review, heb je dat buiten doen? Ja. Ah, oké. Ja, de nieuwe is dan niet in die versie. Dus er zitten allerlei scheidingslijnen in. Ik weet ook wel of er niet heel veel extra budget naar de video gaat. Ja, dat is het denk ik wel. Dus nu toch op 0 gezet? Nou, dat weet ik niet. Dat weet ik niet. Ja. We hebben een hele lange e-mail met dus informatie. Hij heeft een hele lange e-mail. Ik weet niet waar je dat gaat over, maar ja. Ja. Nou, trouwens, ons restaurant is gesloten met een voetbalwedstrijd. En ze hebben wel je reservatie geaccepteerd? Ja, via de website, maar ik wilde net om de reservering te hebben, omdat er huis overweeg kwam. Jij ook persoonlijk. Dat is meer persoonlijk. Heel awkward. Dus we moeten nog even een nieuw restaurant zoeken voor vanavond, ja? Ja, een beetje tijd denk ik ook niet als je... Ja, we hebben gewoon 7 uur. Maar ja, de meeste mensen... Ja, of je gaat thuis. Of je start zo een presentatie of niet? Ja. Hij niet, maar... Dat hopen we wel. We hopen wel. Ja, Rafael zal nu een presentatie starten. Ja. Ja, het is heel... maar we waren ietsje later bij de koffiepresentatie. En toen ging iedereen koffie halen. Dus ja. Ze doen gewoon iets later. Gewoon, er staat een lukken mee. Maar dan moet ik me bellen. Maar dan ga ik naar Special Dependence toe. Ik stuur een mailtje naar aan. Ja. Ik heb een Rafael in staan, geen triple Rafael. Dus een games hier nog heel. Julia Script, ja, daar wou ik eigenlijk nog ook heen. Maar was dit gereden? Zo, dus Fabian. I can't reach the organizer or the talk guy. So I don't know.
He was just here.
Oh, okay.
Yeah. He gave the talk just before the break, so I think his laptop is still there too. So
oh yeah. Everything seems ready.
Should be a good stuff. But talking right after him, and I give up talking.
Don't say that to him. He'll take all your time. I mean, he's basically already eating into your schedule, right? Even without showing up.
We never met in person. No, like, okay. It's been what, like 10 years or something?
Yes.
Yes.
Wait,
Yeah.
where then?
We met at the spatial data center.
We did Esther.
I remember
meeting Esther in Delft.
Yes.
And then you said like, and then I found out that you met him as well.
We're going to SDSL this year again in Prague.
No, this year is not go. I will be
It was this
longer
mix
vacation.
of like
Good.
all over the
Yeah.
like, what the hell are we doing here? And then because one of the angles is 0 to pi.
Felix will go this time.
always hard.
Yeah. That was my latest
Sometimes
slide.
you end up with a blank.
That was my latest slide coming from them. Okay.
Oh, and that's my slides not building. Oh my god.
Okay, do you have them on CI?
I have them on CI. It's okay. We're saved. Hopefully.
Same thing happened to me. I mean, like, I also had to switch to a.
Raphael, I'm
version
definitely
that
making
I
the next presentation for
stored
tomorrow.
somewhere.
Yeah, I don't trust you now.
Okay, well, welcome back, everyone. So this is kind of the middle half of the Scientific Data Mini Symposium. We had a cancellation, so I'm trying to fill it in with one of my talks right after this, but I can give some time back to Raphael, so you have your full 10 minutes or so. So I've been told not to give you too much more than that. So, so if everyone wants to get seated, or and you're ready to go, do you need to debug your slides, or?
No, they're all good now.
All good? Okay.
I'll bang through it. Yeah, I did short talks, so I don't really have enough time to do what I want to talk about. So be fast.
Yeah. I think you need to use the microphone still.
Yeah.
So.
What about this one?
Okay. Without further ado, Raphael.
Okay, so I'm going to talk about what a raster is, dimensional data, and how it relates, disk arrays, plotting, common GIS methods, and then it's not on. And then I'll give an example, some examples. Okay, so first, for people who aren't across it, probably most of you are, I'll just mention what a raster is. Basically, it's an image, but not necessarily RGB. Values of some variable across some gridded space. Usually has X and Y spatial dimensions like latitude and longitude, and with a coordinate reference system of some kind normally attached, not always. But also, a raster by a raster, we may mean a collection of multiple data sets with multiple variables in one object. And they may have more dimensions than X and Y, like time dimensions. Here you can see some data spread along a time dimension. And so to handle this kind of data, of course, rasters uses dimensional data.jl, which was written for that purpose. Extends it, so a raster is an abstract dim array, and a raster stack is an abstract dim stack. This gives us the base foundation for spatial work, and I'll try not to talk about that stuff too much. But what rasters adds is coordinate reference systems, missing value handling, and some other things that are off screen. What can I do here? Oh, there you go. File IO and some GIS tools. And now I can go back. So we have a bunch of backends. So rasters builds on the shoulders of lots of other packages. It doesn't do all this work. So netcdf and HDF5 use NC datasets. Grib uses Grib datasets. ZAR, which is in process, Felix is writing, I think. Getting there, uses our datasets. We have GRD from R, which is just memory mapping natively. And then everything else in GeoTIFF is done by ArchGDAL. So these are loaded independently now, and you just load the package that you need for a specific problem. But rasters will tell you if the package is missing when you load it. Because we have backend detection, constructors will detect what backend to use just from the extension of the file name. So you don't really have to think about it except for loading those packages. We also have disk arrays integration. For larger than memory data, and this is, you've already seen all this if you were at Fabian's talk just before. Basically, we can lazy load data from the web or from disk just by using lazy equals true. The default is in memory, and it will now all warn if it's larger than true and not load the array or error. But you can set this option to load lazily. And then broadcasts and things like that will still be lazy, just like disk arrays works. So you'll finally read data when you index in some way. If you do a get index, you read the data. If you want to keep it lazy, you can use view instead. We can also set chunk patterns now, and this is standardized across the backend, so you can just rewrite a file and specify the chunk patterns that you want, and that will work the same way in GDAL and netcdf. And you don't have to look into their file writing options. We also integrate raster data sources. Mostly I have to talk about this for the example because it's a really easy way of making examples. This is a package that will download files for you and then give the file name. Here it will get WorldClim BioClim. But I've also got that problem again where you can't see the text. You can see we can actually just use this one line to construct a raster with that raster data sources file. So it makes it very easy to make examples and to load common data sources. We also have custom plotting for rasters. A lot of this just builds on dimensional data these days. But the idea is everything is always the right way round and the right way up, which is fairly basic, but it works. So you can just plot in plots.jl, and sometimes the formatting will be a bit off like that, but you get the lookups. You get X and Y, latitude and longitude coordinates that you want plotted. And actually with plots, if you have multiple dimensions, it will tile them. So you'll get time or whatever tiled. That's not possible in Mackie at the moment with how the recipe systems works, but basically plotting 2D things works fine, as you would expect. The cool thing that I'm really into now is that GeoMackie works with rasters. So this is Anshul's work, not mine. But they're integrated, so you can just add a projection to a geo axis and you can plot a raster on any projection that you want. Here on an ortho projection. And that mostly just works. Okay, so the other things that rasters adds that dimensional data doesn't have is a lot of the standard GIS methods. And these are for working with raster data directly or for using vector geometry data with raster data. We have a completely native rasterization engine. This is not using GDAL or anything like this. It's all custom. It accepts all geointerface geometries, so shapefile.jl, GeoJSON, any geointerface compatible package will work and rasterize. It's extremely fast and threaded. It should be an order of magnitude faster than most other rasterization implementations. It also has detailed correctness warnings, so if any polygons are missed or don't change the array at all, you get a list of those back so you can see where there's errors or polygons that are out of bounds from your array. It has consistent behavior and syntax for these functions: rasterize, coverage, mask, bull mask, missing mask, and zonal stats. And then we have a bunch of other methods that are just for working on rasters, extracting points, trim, mosaic, aggregate, common GIS things, and resampling with GDAL. Now I'll just do a couple of examples. How much time have we got left? Okay, cool. I've just made some basic examples, not really to show you in detail how to do these things, but just how easy these things are getting now. I'm really happy with how little code some of these take. A lot of them are half the size of the original docs from 2 years ago. So we have, this is using GBIF and raster data sources. We can get the climate, global climate with WorldClim. We can get occurrences of some species using GBIF. And then we can extract data at those points from wherever in the world they are. This is a really common thing to do in ecology. I think Tim will be doing things like this in his SDM talk in a couple of days. And yeah, from that you get a data frame of values from the raster stack, missing where there's no point in the first place. And things like that just kind of work and are pretty fast. We can also mask. This is masking with polygons, so it's basically masking rasterization. I can make now make a stack of climate data. I'll get some countries from Natural Earth here. This is Anshul's new package. And here we can select, I'll just randomly select Finland as a country from the data set, and we can mask that climate data with Finland, and then we can trim the boundary off it. So we should get a raster that is just showing Finland masked of all that climate data. And, raster data sources. Oh no. It's just downloaded all the data and now I can't see the plot. That's what's happened. Sorry. Oh yeah, there you go. Plot at the bottom of Finland, kind of. Maybe if I squeeze it a bit more. Yeah, there you go. Okay. So yeah, it works. Hopefully that hasn't happened for every single example. Another thing, we've got zonal statistics. So this is basically an abstraction over masking and cropping to give us a really quick way of getting statistics about geometries and the raster data underneath them. So yeah, and it turns out I think it's like an order of magnitude faster than doing this in Python from benchmarks. But here we'll again get some climate data and countries from natural Earth. And this is like just an example of calculating the mean maximum temperatures of all of these countries in July. And I can just do that with this zonal function. Zonal mean of the climate of these countries. And we get what we would expect, Antarctica as the coldest and Kuwait as the hottest in July. And you can do all that in a couple of lines. Okay, I want to thank, again, everyone who's contributed to rasters. It's getting quite a few these days. Any problems, always make GitHub issues, please. One thing with rasters is it always needs a file, and there's so many kinds of files. So if you ever make an issue, try and include a raster file, because it's like just really impossible to know what the problem is without that, if you can link to it or something. Yeah, thank you.
Okay, thank you. Questions?
I would have a question. Is there a way for a user to find out which of these methods that you just presented, like zonal statistics and extraction, which of these work for lazy data and which ones don't?
Yeah, that's a good, I think, yeah, that probably needs to be worked on.
Yeah, I mean, just to avoid bad surprises. I mean,
yeah, we probably need a set of warnings. Yeah, the answer is no, there's none. But a lot of them are lazy. So like things like trim and crop will make a view, so it still works. But yeah, it's not clear which.
There's just something I don't understand with like the syntax. Can you explain those two dots between when you want to select a range? I don't get.
This is just an interval. There's this package interval sets.jl. So some number dot another number means an interval. So it's an interval over.
But why couldn't you use the normal column syntax for an interval?
Oh, that's not an interval, that's a range. So an interval is very specific in that you can specify if it's closed and open at both ends.
Okay.
And you're specifying everything over this interval, where a range actually has values in between.
I see.
So when you're saying a range, you're saying all of these values, but that's not, so that's a different meaning.
Okay.
Yeah.
Okay.
Yeah, I guess that is a bit confusing. There's also a between selector. You can just use between instead if you want it to look.
So it comes from the interval package.
Interval sets.jl. Okay. It's pretty widely used.
Okay.
That, yeah.
It's the first time I see that.
Okay.
Yeah.
How fast is this package? Didn't you do the benchmark against Terra and whatnot?
There's some, but there's so many things to benchmark, and there is an online rasters benchmark, but I haven't done it yet. Some things are fast. Like rasterization is really, really fast. I've benchmarked against GDAR. I think it's 30 times faster than GDAR. And it's about the same speed as fasterize in R, but that doesn't have very many options. And once you thread this, it will be a lot faster, 5 times faster.
Okay, any more questions? Okay, well, let's thank Raphael again. Okay, and the next speaker is yours truly. So give me a second. I'm going to give the microphone here to Fabian, who's going to moderate.
Good.
Okay, so this is a filler talk. Jake McQuinn was supposed to be here to give this, but I think due to unforeseen circumstances, he just started a new job and wasn't able to come. Jacob was going to be our main representative from kind of the Julia data community, but we hope that he'll be able to deliver his talk maybe online in a different way in the future. So just keeping with the theme of kind of what we've heard this morning, I was going to go in and talk about my experience with chunks from a biomedical perspective, and maybe a little bit lower level perspective. What I've done is adapt to kind of a more general talk to kind of tie in with everything we just heard. So, and you can cut me off in about 20 minutes.
Okay.
My slides are moving themselves. Okay, so just a little bit about me. I've been trained as a biologist. Most of my time has been spent training at medical schools, doing kind of biomedicine, mainly more basic biology. Where I've ended up is the Howard Hughes Medical Institute research campus, and maybe our biggest thing there is different kinds of microscopy, namely light microscopy and electron microscopy. And so for us, our challenges there have been kind of, we make the instruments that actually collect the data. And so part of our frustration has been trying to figure out how do we deal with file formats to get the data in the right place at the right time, and so we can efficiently access it. Which is actually a little bit of a frustrating problem because you know you could solve some scientific data problems, but it's all your responsibility. And often our vendors don't cooperate as well as we would like them to. Kind of what I do with that is I take, let's see if that's going to play. Okay, so basically I take raster data that we just heard about, usually 4-dimensional 3D spatial data plus over time, and then use that to model, in this case, C. elegans, a kind of worm. And so there's a lot of processing that went into this. I'm not going to talk about this, but basically I'm just trying to explain kind of what my perspective is as a biologist. Okay, I might just need to speak into it. Okay. So, so mainly what I want to talk about is kind of chunks. Last year at JuliaCon 2023, I mainly talked about HF5JL. And I'm going to talk a little bit about that and a little bit about ZAR and how we can maybe try to put this all together. So earlier this morning, I'm not sure if we really got into kind of this abstract concept of why we're doing chunking, other than maybe wanting to more locally access data or access large data sets out of core. So I'm going to cover some of that initially. Let's talk a little bit about differences between kind of where these chunks are actually stored, and again to some details about what I've been struggling with HF5, and also how this is kind of starting to converge with, say, ZAR-V3 and sharding. I think there's been kind of some evolution in terms of scientific file formats lately. We moved ZAR and these newer file formats have been trying to distribute chunks over many files or objects as they may be. And so that is very convenient in that we can immediately find the data that we want to look at without having to kind of parse a bunch of metadata. But the problem that I've encountered here, and I think everyone who's worked with ZAR, is that these are very hard to move around a disk or your cluster, or you have to deal with some very different kind of mechanisms to move them around cloud storage. And so there's kind of this trade-off here. More lately, some of these schemes have started to implement shards, which are basically super chunks that have smaller chunks within them. But to me, this seems like going around in a circle. First, we took individual chunks, broke them apart into individually addressable files, but now we're putting all the chunks back together and starting to look more like NetCDF or HF5, which is where we started in the first place. And so it sounds like we're going in a circle. So what's going on here? Although I think one advantage here is that There is some potential for maybe reading multiple chunks at a time, if they're sequenced in a certain way, if there's maybe they implement some kind of space filling more to the C curve. And so there's potential for further optimizations there, which is kind of what I was asking Fabian about earlier in terms of do we need another interface to kind of make a second order abstraction. And so I think I probably covered a little bit about this in the last slide, but you know, there are some problems with trying to abuse a file system to be your local key value store. You know, file system is doing a lot more than just identifying where data is. You have all kinds of ownership and permission issues, especially if you're on like a Windows-based system where most of my devices, acquisition devices run. Windows is particularly has high latency per file access. I think I measured the stat calls are about 100 times slower on Windows than they are on Linux. And I don't really have a choice where microscope manufacturers implement their drivers and software. So that's been very frustrating. Something that happens that, especially on Windows, you have to make separate API calls to access different files, and that can quickly add up when you have, say, 1 million files. Something that's nanoseconds versus microseconds quickly becomes seconds to minutes. And ultimately, you don't actually control well where the chunks are on disk. And so you can't really do a lot of optimization in terms of reading multiple chunks at a time. On the other hand, if we try to put all the chunks together, then we need to figure out how to locate them in that file. And this is kind of the whole problem that something like HF5 was supposed to solve. There was supposed to be, this was supposed to give us a standard way to organize a file in a hierarchical fashion. So as Fabian talked, this is basic. This is a slide before. I knew I was talking after disgrace, but basically we need an interface to access chunks, and I think maybe we already just heard it this morning. But I think there's also kind of front-end access, like how much is the user supposed to know that there's chunks, and how would that change the algorithms that use these? Or do we put this more behind a low-level access way, and perhaps we have two different interfaces to access chunk data? So there's been some differences now that support things like SAR, in that we now have these key value object stores, which look kind of like file systems, but really are not. They basically get away from some of these per file permission issues by creating buckets for authentication. They have keys that look kind of like files and directories, but are really just a flat space. But there is something kind of interesting in the implementation of these cloud key value stores, in that they just use regular HTTP, and there's this potential for accessing parts of files over a request. And we can just take a look at that. This is just a normal HTTP request. And part of the thing that I really want to point out here is that there is this range parameter. And so what this allows us to do is ask a remote web server for a specific range of bytes. And so now this is starting to kind of get into, well, if we knew where the chunk was inside of a larger shard or larger file, then we could just retrieve it almost as efficiently as if each chunk were in separate keys or separate objects. Okay. And so bring that all back around, I started to think, okay, well, how about HF5, which is the file format that underlines netCTF? And what is keeping HF5 from being an efficient data store? Why did we have to come up with SAR to get around problems that we were having with HF5? And kind of looking at it and looking at interfaces for there were several ways to kind of get to chunks. And for the most part, HF5 just prevents a high-level interface. It doesn't want you to think about the chunks underneath. You have to actually go through quite a bit of of hoops to kind of get it to tell you what's happening or where the data even is in the file. It just wants you to directly index into array. But so there's these several legacy functions here. And more recently, they introduced interfaces that allow you to actually read things at the chunk level, although it almost seems a little begrudgingly done. But if we look at that, basically these interfaces do give us kind of offsets into the file. And so that looks kind of promising. It looks like we should be able to receive raw chunked data. But I think part of the problem here is that the way the HDF5 library is oriented is that it usually requires us to do what's on the left side. It goes through the whole pipeline for us and doesn't let us think about what's happening at a lower level, or basically how the file's organized. Whereas SAR is completely different, right? It basically doesn't do any of this pipeline for you automatically. It's really just this file specification or object source specification. And we really just want to be able to directly access chunks on the disk. And part of this is also kind of some of the underlying thinking of how things were going to be organized. They really went deep into B trees, and this makes the HDF5 metadata complex. Got ahead of myself there. This makes some of the HDF5 metadata a little bit more complex than you would think it should be. And so after kind of doing a deep dive into the C library, something I found out is there are more efficient ways to access chunk data within HDF5, where I want to get information on where all the chunks are. And basically, HDF5 has two kinds of APIs. One is to get information on the individual objects, but this is very slow because every time you ask for the nth object, it does a search through its metadata to try to do that, and that becomes very inefficient. Whereas what we really want is the iterator. We want to be able to maybe go through and possibly get all the chunks that exist, instead of restarting a search every single time we ask for the nth chunk. And so it turned out that it existed eternally for HDF5, but they weren't exposing it. So I found someone else that actually found this and basically did a bunch of work to push this all the way through to now expose this as a public interface. The only problem is that for the Python folks, this is really, really intimidating because it requires you to pass in a callback function. For Julia, this is a little bit easier. We could create a C function that could act as a callback, and so we could use these iterators. And it turns out that this solved the kind of huge problem of scaling that I was encountering, because as I mentioned, there were all these older legacy functions that allowed you to access this chunk information, but if you scaled up to about 60,000 chunks, this would be incredibly slow. But now with chunk iter, this is much faster. You have linear scaling. And just kind of looking at benchmarks as what were the access times with this, you can see that basically we're not. This is an exponential plot, sorry, a logarithmic scale on the y-axis. That basically now we have much better scaling as the number of chunks grow. And it turns out basically this was now really important. It solved a lot of problems with how other people were having with accessing chunks in HDF5 files. I worked a little bit with some of the BLOS folks to kind of make this fast, and so now PyTables has implemented this as an accelerated method for getting data out of HDF5. In HDF5JL, I implemented this as a kind of surface function, get chunk info all, as opposed to just get chunk info. So this allows you to kind of retrieve the entire vector of chunk info, which will tell you where all the chunks are within the HDF5 file. And now if you think about that, combining all that together, if we now know where all the chunks are in the HDF file, then we can completely forget about HDF5. We can just go into the HDF file, access a certain byte offset, and retrieve the chunks, just like perhaps we're using for SAR. Now, strangely, SAR started going back the other direction, which is they started thinking about how do we take a bunch of chunks and reduce the number of files, for whatever reason, and now put them back into one big file, which sounds a lot like HTML5. It's a little bit frustrating to watch because I think it wasn't clear that the people writing this had really studied HTML5, and so it looked like they were starting to make the same mistakes over again. But eventually they came up with a fairly simple format, which is you could just append to the end of the file where the chunks are. I thought that was pretty good, but it was missing one critical thing that HTML5 did have, which is right at the end they have a checksum to maintain the integrity of the data. Because if your chunk index gets screwed up, or maybe it's not what you think it is, then you can't read it at all. And so kind of after working with them, I tried to make it a little bit more similar to HTML5. We added the CRC32 checksum. And this thing actually looks like almost identical to an HTML5 data structure. But now this has been implemented in SAR v3 as the sharding codec. And so now this is now available. So now I think we're basically getting to the point where the HTML5 and SAR v3 interfaces starting to look really similar. I know how to get the chunk indexes, offsets, and sizes for both these. And now perhaps we could just write a general thing that could read either HTML5 or SAR. But what happens? Sorry, my touchpad's really sensitive. But what happens if we could just use them at the same time? What happens if we could have a SAR shard that could be simultaneously an HTML5 file and a SAR shard? And it turns out that's possible. So it depends how crazy you want to be. As I mentioned, the shard trailer is actually pretty similar to the HTML5 structure. So we could actually have HTML5 and SAR share the same data structure. The only difference is I need to teach SAR a slightly different checksum codec. For some reason, the HTML5 went with something called Jenkins lookup 3 function instead of CRC32. But that said, we do have a Julia implementation of this weird checksum function, so it's not a huge problem for us. It's in JLD2 at the moment. And so you could think of basically a file that looks like this. We have a little bit of HTML5 header that just points at maybe where the chunk metadata is, could be at the bottom. And then basically we have the SAR shard trailer right at the bottom of the file. And this is perfectly compatible. Both HTML5 and SAR are perfectly happy. And so we're starting to get convergence of these two things. Okay, so I looked at this and I was thinking about, okay, there's one other thing that I think a lot of my crossfits fight me with about is like, why don't I just produce TIFF files? Well, I looked at TIFF a little bit, and actually, I think we could actually have a file that's simultaneously a TIFF file, an HF file, and possibly a SAR shard, which would be, I think, fantastic because now everyone could read it however they would like. The reason this is possible is that HF5 has a mechanism to offset its header data at 2 to the n bytes after 512 bytes. So you can put it at 1 kilobyte, 2 kilobytes, etc. And all TIFF requires is a few bytes at the very beginning that points to image file directory metadata. Now the one problem is that TIFF usually doesn't deal with 3-dimensional data, but that I usually end up collecting through a light sheet microscope, or rather my colleagues collect. But it turns out there is some obscure TIFF tag for encoding tiled depth. And so it's very possible that we could actually have even volumetric data shared between TIFF, HF5, and SAR shards if people can recognize this additional TIFF tag. So I think in summary, I think this solves a particular problem that I have with scientific data, in that there's a proliferation of file formats. Everyone seems to come up with their own, and more so, different fields don't really communicate very well, and end up re-implementing very similar ideas over and over again. I think if one kind of is able to look between fields, and I think Julia is actually a great language for exploring this stuff. It's been great to kind of go between different file formats, different interfaces, to be able to kind of interrogate how this works. Okay, So I think I'll finish there. Basically, we've been using SAR because there's some advantages to having one file per shard. It's very simple. It allows you to access individual objects. But this very much depends on the underlying storage system, especially if it's a Windows file system. But now we've implemented very efficient direct chunk access that we can access from Julia. And maybe this is actually mappable to the same kind of concept with SAR shards. And so I think we have an opportunity here to converge multiple paths here and possibly kind of just create a single interface that can maybe handle everything. And so I think the main reason that I haven't implemented this arrays is because I've been trying to solve this problem with HF5. I've done it now. It required writing some C, but it's done. And so I think we're just about to do that. So thank you, and take any questions.
Okay, so other questions? If not, I would have many, but the first one would be, how do you think your work relates to what the care chunk people are doing? I mean, because that's really a very similar approach by basically, they basically build catalogs of like all the chunk positions inside HDF5 files and index them and then access them as if they were a SAR. I mean, like so how do you think about that?
Right. So Circular Chunk is a Python library that basically tries to generalize over chunk interfaces. I think it is related in that it has the same goal of trying to extract out common chunk information, but usually as a separate file, as kind of an accessory file. Whereas what I'm doing is trying to actually not have these accessory files because that seems rather fragile to me and things will quickly get out of sync. And so in my case, I've been trying to implement it as part of one file. But I think it's very related. I think I have code in chunk as well, basically as I've discovered how to make these things more efficient. And so they're also using that same method to efficiently extract chunk information from HF5 now. Although now it's so fast that you don't necessarily need to do that. It's a kind of discrete step.
With all the technical challenges, how much thought or experiments have you done with API ideas for using the chunks?
I haven't really, right? I was just trying to get it to the point where for common file formats that were before me that I could efficiently access it. And I was hoping Fabian's exploration of disk arrays would take care of the API side. Although I do see a little bit of problem with maybe the sharding. Potentially because there could be some advantage for like pulling a whole shard down and keeping that cached. But I think it could also possibly be kind of a nested disk array implementation. But those are hypotheses that I have at the moment. So.
Yeah. Okay. Are there more questions? Okay, then let's thank Mark.
Okay, we have another small break, although it's not a whole conference break. And then I think we have another 3 talks to finish up the mini symposium. We could use this to discuss, or you guys can take a bio break. Okay. PDF on the resources. Would that be possible? I think so. I haven't used it yet. Okay, so I think this last segment of the Scientific Data Mini Symposium is going to get more into applications. So I think we're going to start off with Romeo here. He's going to talk about ksvd.jl and how you got a huge speed up. So.
Yeah, all right. Thank you everybody for coming. So I'm Romeo. I'm a PhD student at Stanford. And I'm going to talk today about my implementation of ksvd, ksvd.jl, and in particular, how I got 150,000 x speed up over the baseline implementation. I just want to spend 1 or 2 minutes talking about what is ksvd. So just really quick, ksvd is related to the SVD algorithm, singular value decomposition. So we're kind of the domain of linear algebra. And what we will be doing is kind of speeding up particular linear algebra operations, in particular sparse linear algebra. So what the ksvd algorithm does, you have a data matrix that is kind of has a column of data, and then you have a lot of columns. Each data sample is one column. And you want to find a new basis for this data. And you want to find a basis such that you can actually represent each of the data samples by only summing up kind of a very small number of basis vectors. So typically what you do, for example, with SVD is you can find a new basis that's orthogonal somehow, but in the end for each sample you need to sum up actually over all the basis vectors. And we want something that only sums up over a very small number of basis vectors. So you can kind of see that there's the sparse component of this where you multiply the sparse assignment matrix with the dense matrix. And that's kind of a theme in the talk today. So why is this important? So why are we using this? So actually my research is on understanding how vision and language transformer models kind of work and doing a safety assessment of them. And so one thing you maybe want to do is you know that in an image transformer, for example, you have these very high dimensional embeddings. And there's this theory that says, oh, actually, every embedding, even though it's very high dimensional, is representing kind of a few discrete concepts that are in superposition to each other. So what you're trying to do is you try to disentangle the embeddings, and you try to say, oh, actually, this embedding is only made up of a few kind of components which we can understand as a human. And so if you can do this, you can kind of do interpretability of these large language models, for example. And so I'm not the only guy who's working on this. There's this company, Anthropic, maybe some of you know it. They're kind of an OpenAI competitor. And last year they were also publishing a paper that does something like this. And they say we want to do this for a large data set, maybe 1 million samples or 1 billion samples. Actually, this is kind of a known problem. And there's this algorithm, ksvd, but it's too slow, so it doesn't scale to the sample sizes that we want to do. And so Anthropic said, oh, we're going to give up. We're going to do some kind of gradient descent-based algorithm, even though the theoretical properties are much worse. And so I said, okay, I think the problem is not that ksvd is too slow. I think your implementation is too slow. So let me go ahead and see if I can make a fast implementation. And so this is where ksvd comes in. So by doing a bunch of work, and I'll just briefly touch on it, we were able to get about 150,000 times speed up. So here's a graph where you can kind of see I started off with this baseline implementation. And this was actually already Julia code. So this is written by this Japanese guy 7 years ago. And it was basically the paper taking all the equations from the paper, writing it in Julia and running it. And Julia is reasonably fast. And I looked at the algorithm and I say, okay, we need to get this like much faster. And I think we can actually get this parallel if we do a few algorithmic modifications, kind of change the algorithm just a little bit, and then work a lot on improving the kind of computation. And so by kind of repeatedly doing improvement, and measuring a lot which improvement actually help, you can kind of see this performance curve to kind of the speed up that we get over here. So before I talk about how we get the speed up, just really quick, if you want to use the package, you can just install it through the Julia package manager. It's registered. And so you can get your data embeddings from wherever you have them. And you can just run ksvd, and that's it. We're putting a bunch of effort into making it nice to use. And then there's also some more options if you want to get into more detail. And we'll, for example, talk about a little bit the executors that are kind of inside of this method and how you can dispatch on different execution strategies, different parallelization strategies. We'll get to this in a second. So now I want to take just a little bit of time about talking about the main algorithmic techniques or the modification techniques that we did to optimize this code. So actually, most of a lot of the speed up comes actually from algorithmic modifications. And so what you want to be thinking about is how can we kind of rewrite the algorithm to make it maybe reduce the number of required computations and also make it more more feasible for threading it onto many tasks, reducing communication, trying to reduce the memory movement and so on. And so there's this kind of mixture of doing logical changes to the code and trying to look at the equations and rewrite the equation somehow. And one thing that's kind of very important there is that sometimes, or most of the time, you can kind of come up with different ways to compute something, but you don't really know what's going to be faster on one core, what's going to be faster on many cores, what's going to be faster on a distributed system. And so one thing I want to be pointing out is that benchmarking really is super important, and I'm going to show a little bit how we do this later. And also another thing, which is what we did, which is quite nice, I think, is you can have these kind of Julia types that you put in as a strategy at the top. So actually you say, okay, this time I want to run KSVD, and the sparse coding method, I want to use kind of this type, this execution type. And then later, when you implement your sparse coding, you can dispatch on the different strategies that you have. And so you can kind of do different things, and then you can measure if something is faster or slower, something is faster on many threads, and so on. And that's very important, and gets you kind of a lot of overview over if you're actually improving your code or not. So these algorithmic modifications get us about 600x speed up, which is pretty good, and then we get another 250x through kind of more code-centered changes. So there's a lot of reducing the number of kernel calls mostly being buffer allocations or memory allocations, so you can get like a lot of speed up there if you measure and you see, okay, actually we have a lot of overhead there. Of course, you want to make sure everything is threading nicely, and also this topic of buffer allocation and threading is a little bit complicated. And there's this package, Oh My Threads, that has a great kind of section on how you can deal with pre-allocating buffers in a multi-threaded setting, because Julia as a task migration is a bit complicated. And then we want to optimize cache hits. If everything else is really, really fast, you want to kind of see we have a memory-bound application, and so we want to optimize the cache hits. And so this is really how you get the last drops of performance. And for this, I want to talk about one other package actually, which is threaded and sparse mobile. And I don't have so much time to talk about this today, but I have a poster, and so you should come check out my poster if you want to see this. So we found we want to kind of do this type of multiplication, dense matrix times sparse matrix, and we want to do this multi-threaded. But everybody else only does sparse times dense, so kind of the opposite thing. And actually, there's no threaded implementation for this, even Intel, I didn't see one. And so we implement this, and this turns out to be actually much more cache efficient than this way. And so we're able to outperform NCal sparse even in kind of their own domain by about 2x, using very few lines of code. So there's this package polyester.jl by Chris Elrod, and it's like amazing. And you should check out my poster, I'll tell you more about it. All right. So let me just show you one slide. If you're getting started with like optimizing your own application, I can definitely recommend starting with profile view to get kind of an overview over your application. This is not my picture, but something like that. But what we've also done is to use timer outputs, and you can kind of go in and you can actually add a timer to kind of every method that you're using, and then you can enable the debug timings like this, and you can get a super nice overview over where your code actually spends its time. And now we can again go in and you can kind of dispatch on these different methods, and you can see for your application, for your executor, how fast it actually thinks, what actually does take the percentage of total time. And so if you do end up using this and you really want to squeeze performance, I recommend that you put in a few different of the executors, different of the parameters, for example, the chunk size and so on. And you can kind of measure very easily how you're doing. All right. So short time, short talk. I just want to say thank you to a few people who kind of wrote packages that really helped me. So the profiling package is super nice. Oh My Threads, which is a pretty recent development, but they have also some great tutorials on how to do multi-threaded kind of buffer replication. Of course, polyester gets me the speed up in the dense sparse setting. TSVD, a very nice SVD implementation from like 7 years ago. Yeah, and then I think you should all come at, was it 7 p.m. To check out my poster on threaded dense sparse mole. And yeah, that's my talk today. Thank you.
Thank you. Any questions?
So I'm not so familiar with SVD, but what is your opinion on the SVD that's just in linear algebra? We use that all the time, but I see you also mentioning TSVD here and your KSVD. Like, how does it relate to each other? Is it like for completely different problems, or is it like a faster implementation for certain problems?
So the problem you're trying to solve is a little bit different, but it's related. So actually the KSVD algorithm uses SVD inside of it, but you only use the first like main principal component, kind of the first singular vector. And so actually one of the speedups from here to here, you can see this whole brown bar goes away. Why is it? Because we replace SVD with a kind of something like a power method that only computes the first component, and this is actually TSVD, which does it for us. And so you end up using this kind of SVD or whatever many times at each step of the algorithm. Then you use maybe, let's say, 1 million times or something like this. So this is the relation of the typical SVD and kind of the KSVD. And the reason for this is because actually kind of SVDs, you can think of it as kind of a convex problem where you at each step can kind of minimize a little bit better. But the KSVD has like a very discrete nature. So there's these sparse assignments, and it's not so easy to kind of just take a step, whether it's some kind of Newton method or whatever, to compute your minimum. So you have this kind of very non-convex character to it. And this is why you have to loop many times around SVD. And also why I think, and have also shown, that the Anthropics sparse autoencoder gets actually worse results because it's gradient based and it can't really do the global search of minimum as well as this can.
Okay. Thanks. Yeah.
Thanks. Yeah, thanks for the talk. Very interesting. You use polyester. Is lock, is that an issue? Locking objects?
So
since you use threading.
Yeah. So that's a good question. So the question was locking, like writing to memory, for example, pre-allocated buffers. So that is something that we have. So what we ended up doing is we do these kind of mini batch approaches where you always say, okay, you focus only on the first, let's say, 20 columns, and you do each thread onto one column. You write into a copy buffer, which doesn't need to synchronize, and then you synchronize. You kind of spread the result again between all your threads. And if it's on one kind of node, this is pretty fast, but you kind of separate away writing to the copy buffer and then syncing. And now if you want to go distributed, you have to kind of do this again. But now we're all the time memory bound, so now you maybe want to have one hierarchy level higher. You do maybe 10 of these updates on different nodes, and then you sync. And this is something I'm also working on right now, but I'm also a bit like, it's fast enough for my application, so it's fine. But yeah, this writing to buffers, and especially in distributed, it gets quite interesting, and there's some trickiness there for sure.
Okay, if Christoph is in the audience, could you get set up? And meanwhile, are there any further questions for you, Christoph? Okay, well, thank you. Let's thank Romeo again, and make sure to go find his poster.
Download it on the pre-tag.
Uh-huh.
Or I can run from mine.
Either way, I'm not sure we got that computer to work, so.
Yes,
Oh, do we? Okay.
Yeah, well, the cable's there, but it's too short. So I will just
Okay.
use mine.
Apparently it's out of power, and we don't know how to charge it.
Yes, and the cable's too short.
I see. Could we optimize that? You want to try to plug it in, charge it, or you? Okay, we'll see if it works.
it's kind of change it. It should go. It's unified. Normally it works. So, but perhaps it's better.
We still need to download the talk.
It's on the pre-talk. I have a USB. It doesn't connect.
Program.
Yes, this one.
This one.
Yes, I'm gonna use the presentation. So just tell me if I can do the full screen. And I'll be
Something
happy.
like F11. Yeah, F11 does this, but
There's something else.
it's not yet.
Not yet presentation mode. Maybe you should. Maybe have to probably download it. I don't know how it works. Presentation. Yes. Correct.
Okay. Thank you for team effort there.
We still got like 2 minutes.
Yeah.
Okay, this will be mine.
Is it on? You might check.
One.
One of the luxuries of running a mini symposium is that we could actually build in breaks, and so I think we've taken great advantage of that. Okay, I'm just going to briefly kind of do a brief introduction. Christoph is a professor at the University of Warsaw, and he has a background in experimental nuclear physics. So we're looking forward to his case study here of using Julia in that field, and I really look forward to your talk. So please go ahead.
So, hello everyone. This is my first Julia conference, so I wanted to go for a short one. So this will be without my many details. So the thing is, what Julia can be used for in nuclear physics, and how do I use it? So this is kind of an entertainment part, just for a couple of minutes. Nuclear physics is somehow specific, even from the, say, quantum mechanical point of view, because it's too small to be treated in a statistical way and too large to be solved exactly. So this is kind of an issue, and the same goes when you look at the size of the team, size of the data, and everything else. It's like kind of in the middle between large projects when you have many people working on, for example, data analysis, whole teams, groups, and very small projects when you don't have to, for example, take care that much about efficiency and things like that. So what we need, this is a list of what we need. We communicate on the really low level with some electronics. We need performance. We need some tools to analyze the data. Usually they are in forms of arrays, 1, 2, 3 dimensional. sometimes images, databases, and things like that. And typically the tools that are used now, and there are spread of, there are different languages used. So there is a C, C++, and root, which we'll hear about in the next talk will be about this one. And then people switch to Python for convenient data analysis, the exploratory data analysis and visualization, and a lot of really homegrown software with different quality is involved, unfortunately. So before I go to the Julia part, I will show you more or less how the experiment looks like and what can you expect. So this is just one example. There are many experiments, hundreds and thousands. So this is, but I hope it's pretty much generic in many ways. So we have to start usually with some sort of reaction to get something new. So this device here shown is a target chamber. This is in vacuum in reality, and you have an ion beam of oxygen 18. There's a small fraction of oxygen 18 in the air we breathe, but you can make a beam only out of this one, and you hit just a piece of gold. And what you expect to happen is that if the energy is big enough but not too large, these two things will melt together, form a new nucleus, and this nucleus then will go through some sort of decay. For example, it can split into two smaller nuclei and emit some radiation at this time. So to learn what happened, you have to measure all that radiation that is coming out of this system, and this you surround this with detectors. So there's this target chambers inside of this ball, and there are a lot of cables hanging around, a messy thing. And in front you see some germanium detectors which measure, for example, gamma radiation. There are other types of detectors involved as well, but all these detectors then are connected to the electronics. So each detector has its own channel. This is analog signal. The integral of the signal tells you about the energy of the particle you detected. It goes through a series of operations. At some point it gets digital, then it's got analyzed by the FPGA, and in the end you want to read that energy and time, which is somehow calculated inside. So for example, we have about 150 detectors. Each one is counting 10 kilohertz, 10,000 events per second. These channels are grouped into modules into crates, and then you connect this to a PC by some sort of interface, and this is a place where Julia can come in, finally. So usually these digitizers, they have a C library provided by the manufacturer, because this is kind of a standard. So first thing you can do with Julia is to easy call C functions without any extra cost added on the top. So this is just one example of communicating and just retrieving some data from this digitizer. You can also, then you can decode the data, which are usually tightly packed. There are some binary patterns you have to know from the documentation. You can unpack the data also using some low-level operations in Julia. Next thing is to translate the whole thing into some physical meaning. And that involves translating the answer of these digitizers into physical units. So we usually work at the level of picoseconds, which is 10 to the minus 12. That's the kind of precision we expect. And then all these events are grouped. This is called event building. So the beam is pulsed, so every time the beam comes every 100 nanoseconds for a very short time. So whatever radiation comes out of the system has to be kind of connected with the beam pulse. I want to see what happens when the beam hits the target, not just some random things. So we do that, and this is just a piece of code, some example how it looks like internally. So this is just old style programming, some loops and conditionals, and nothing special about it, but it has to be quite fast. And finally, once you have these individual hits somehow connected to things that come together in reality, in physics, you can create histograms. And so these are usually 1 or 2 dimensional spectra, which will tell you that some sort of radiation was coming more often than the other type, or which radiation came in together with other energy. So we can study this is like fingerprint of a nucleus, which was there created, and you can figure out what was that. So for storing this spectra, the histograms, we use HDF5 files. So there are, again, some examples of the code, some pieces. But also sometimes we go to so-called least mode data. So instead of having just a spectra where some information is lost, we store everything about these time-grouped events in some custom binary format. So again, there are just some structures which they have sizes of field as needed, so they are optimized in that way, and then we just write it down to the disk. So everything is there, but if you want to get a picture out of it, you need to go through all that data to find the events you want to find. And in this case, it's also done in Julia, and it uses multi-threading, multi-processing, and even distributed computing without referring to high-performance computers. It's just some random laptops which were found in the cabinets. They can be used for that, because the bottleneck here is actually the access of the drive. So if you have some even old laptop with weak CPU but with a SSD drive, you can make a network of that stuff and just put their names into machine file and run them, and this scales in a linear way. The more you have, the faster it gets, because this is a very simple case when this multi-threading or multi-processing can be broken into really segments that do not talk with each other. So each one does its own operation, and you just get the results from each machine, each process. And finally, once you've done all the analysis, you want to do some finalizes or publish your results. And here comes some other group of packages we use: data frames, LSQ fit, which is for function fitting the least square method, hypothesis test from some statistical features, and plots. All these plots were made with the plot package, and the one on your right is for example, is an example which comes from the paper which was published. So this is like a final quality images with all the nice features. You can find them there. Okay, so all in all, it looks like Julia provides everything we need. I mean, we can stop using 2 or even 3 languages like we used to, because there was a C and C++, which is similar but not always the same. You need some expertise in that, in many, let's say, small things. You don't need a Python anymore, because the flexibility of Julia and the possibility to use the REP for exploratory data analysis just removes that. And so everything you have in one language, and at the same time, it's the performance is very good, and there are some plots. There's no time to go into detail, but there are some benchmarks made the same example but with different languages. There's some list of my complaints, but some of them were already answered, and some of them will be answered in a minute or so. So good to be here to learn those things. So thank you very much.
Okay, thank you very much. Jared, do you want to get set up? Are there any questions for Christoph?
What was the research question you were trying to answer, the particle beam?
In this case, the question was, when you fuse those two together, how the fission proceeds. And actually, by surprise, it doesn't split into two similar nuclei, but to a larger one and a smaller one, which is quite unusual for this kind of reactions. So yes, so that was the research question. Yes. Oh, uranium is well known for the heavy and the light one, but this kind of reaction should end up in splitting into two halves, but it did not. So there are many things. I mean, the nuclear physics understanding of how the fission proceeds that we're still missing. So.
I think I've had a very similar experience to you in terms of flexibility and versatility of Julia. One thing I've sometimes encountered is that Julia is a little bit too versatile, and so it's very easy to say use multi-threading with HTML5 and get in trouble. Have you encountered any kind of issues with parallelization?
I mean, this is a very primitive example, and I would say this calls for multi-threading without. I have logs there just because the one process has many threads and it's updating some result. But so I had to put logs for that, for sure. But otherwise, this is really like a textbook example. I mean, this is where you should use parallel computing because you can break up into pieces which do not communicate with each other. So each one calculates the answer and then just returns you practically one number. And this is a very nice, very simple case of using that. But I must say, I've tried in Python. And I failed on the global interpreter log level, and it wasn't easy to overcome this. While here it was just I've changed map to pmap, and that was the end of my job in terms of multiprocessing.
Great. Well, thank you again. Let's all thank Christoph for sharing his experience. Okay, and our final talk of the session is Jerry Ling. He's going to share about using Julia in higher energy physics, and particularly unroot.jl. So Jerry, thank you for joining us, and I look forward to your talk.
Thank you, Mark. Does this mic work, or I have to hold this?
That's working, yes.
Okay, gotcha. Hello, my name's Jerry. Thank you for being here, because there's also a very interesting talk by Lilith going on about the public keyword, so thank you for being here. So my name's Jerry. You might have seen me using my GitHub handle, and I'm a PhD student at Harvard with one of the particle physics experiment at the LHC. So I'm obligated to tell you a little bit about what we do at CERN. In this particular experiment I work on, we have about 10,000 physicists at CERN using the facility of Large Hadron Collider to study fundamental interactions at the highest energy scale. Here you're looking at a satellite image of basically the site, and the biggest white circle here is how large the tunnel for the collider is. Here's a different angle of that view, and you're seeing here the 27-kilometer in circumference collider tunnel. And we have basically two beams of particles circulating in them, and they would collide at some of these collision points. And our experiment Atlas sits at one of them, and this is really giving you a sense of scale. So this detector is huge, 44 meters long, and then about 25 meters tall. You can see people here for reference. You can barely see them. So what happens at the collision point is that the detectors have millions and millions of readout channels, and when the collision happens, all sorts of things coming out of the collision point, and then the detector basically take really fast snapshots of them. So at the millions and millions of readout channels combined with extremely high collision rate, even though we kind of try to trim it down to about 1 kilohertz, we still have a colossal data set. So from these raw detector readout, and with a complex data processing pipeline, you reconstruct basically physics objects into a table-ish kind of thing. So think of a big table where each row is one of these interesting events you want to analyze. So now you might ask, okay, hold up. This looks way too complex for just a table of numbers, right? How do you like represent this kind of process in just a few numbers? So the answer is you don't, right? So let's try to conceptually walk through the type of data we need to represent inside this table-esque container. So let's focus on just a single event. So here you can think of the row as a single event. And let's focus on the electrons in the event, right? So the electrons are reconstructed by the software and then are illustrated as green line here. So think about what kind of information we want to encode in just a single row. So maybe you want to know how many electrons there is according to the reconstructing software. Oh, okay, that's easy. You just have a single scalar. So this is your normal table stuff. But then every single electron may have like a quality attached to them. These may represent how confident the reconstruction software thinks this is a real electron, right? So now you have a vector inside a row. Okay, maybe not so bad. But then you may have other associated information. For example, your electron would basically leave a collection of hits inside your detector. So you may have layers of detector and the electron have multiple hits. So you want to know which hits are associated with this particular electron I'm looking at. Now you suddenly have a vector inside just a single row, right? So that's already a bit mind-bending. But then physicists love special objects because we deal with objects that have physical meaning. For example, for every electron to represent the kinematics, often we talk about these 4 vectors, which mathematically they are Lorentz vectors. So you have basically inside a row, you have a vector of structs going on in there. So all this is to say is that we have quite complex and hierarchical data structure that are required to basically represent our data set in particle physics. So there are essentially these 2 challenges. One is you have immense data size, as I alluded to before, and then you have this extremely complex hierarchical data structure. And remember, keep in mind that this is basically 25 years ago when there was basically nothing kind of available in industry and certainly not a standard. So basically the solution CERN came up with is they wrote a whole software suite for it, and along with it, they invented a data format. So the software is called root, and the data is .root files, very creative. So if you look at the source code breakdown of root, you see millions and millions of lines of code. In fact, this probably has more lines of configuration code than a lot of the code base out there. It's huge and it is monolithic. So in this talk, I'm not gonna talk about the root framework. I'm gonna focus on the file part, the file format part of the root ecosystem. And even when you focus on the root files, you realize they're more like file system because they can contain directories and they can basically serialize arbitrary C++ objects, which is another rabbit hole you can get into. But today we really gonna focus on 2 main objects. They are T-tree and Rn tuple. So these are used to represent these table-like object I was talking about, and they are responsible for storing petabytes, I think soon will be exabyte of physics data the LHC has. And one of them is legacy from 2000 to about 2025, and hopefully Rn tuple for the future. I'm gonna touch on both of them in this talk. So the rest of this talk will be broken into 3 parts. The first part, I talk about some common performance techniques for reading both of these. So these are, Julia-related things, and I will show them the user experience of reading the data and also the performance of them. Then I will venture into a little bit of this new format that's upcoming, the Rn tuple. I'll tell you very briefly what makes it better and why is it like a modern format, and then how we are basically reading it from Julia. And then the third part is the newest thing that we try to have a capability of writing them out from Julia, of course, without using any of the existing C++ stuff. So let's do the first part first. So in the end, as physicists, so I am a physicist and I do analysis, so I kind of know what I want to have quality of life. So basically, when we are dealing with really complex data structure, sometimes your algorithm is most naturally expressed in just loops. So basically, we want the loops to be fast, but at the same time, the data are usually trivially parallelizable. You're just analyzing your data and then writing them out into sort of histogram or something to analyze. So you want the multi-threading to also just be as easy as you slap on a threads macro or using a polyester.batch or something like that. So we want all of these to be nice and fast. So there are really 3 main things for making the experience good, and these 3 are the most important ones. I'll go through them very quickly. So type stability is probably the most familiar concept to the Julia users. Basically, when you look at this for loop from the compiler perspective, maybe, you realize that the compiler needs to know what event.electron underscore 4 vector is to be able to really kind of compile the most specific method in the loop body. So for this, what we have to do is we need to encode the name to type mapping relationship in the type itself. So think of name the tuple, basically. A second thing is that these tables, because how complex and different types of objects you have in a particle detector, they often are very, very wide. I'm talking about more than 1,000 columns. And at the same time, users often are focusing on just a subset of them. So what you don't want is you don't want every iteration for the library to read the entire row, because that would be a waste of time. So what we do here is we delay this materialization. Essentially, the first line here, when you are just looking at a single event, nothing is actually read from the disk. It's just making a marker here saying, okay, I'm here on this row. And then when user actually index a specific element in this row, we go fetch all the data from the disk. That's actually not a very rare pattern. So for example, if you're familiar with struct arrays.jl, there's a lazy row there. The reason we're not using it is because they have a pretty strict constructor defined. So maybe in the future, we can refactor and unify the pattern a bit more. So the final thing is a little bit specific to the format itself. So this is only relevant for a columnar file format. So by columnar, I mean that if you focus on a specific column, and then you want to say, I want to read a single row from it. A columnar format is where, when you do this, you are basically forced to read more than one row, because multiple rows are bundled together in the column. So what you have here is, if user is reading this row, and you have to do all the work for this chunk, then the most likely thing that's going to happen next is the user is going to read immediately the next row, because they're probably in a loop doing this. So what you want to do is you want to catch each of the chunk per column. So, however, there's a little bit of a caveat here. To make this whole thing thread safe, you need a catch not per column, but also per thread. So initially, this was done with the classic buffers thread ID pattern. Then when I was redoing this for R and tuple, I saw something really strange. So I was like, okay, is this still the way to go? And then people suddenly realized there are so many code in Julia that was doing buffers thread ID. So we had a really long discussion in the Slack, and then in the end, there's this fantastic PSA blog that you should read if you haven't. So we need a new strategy. So our new strategy is, in addition to the collection of buffers we have, we would have, in addition, a collection of logs. So whenever a task trying to update or flush a buffer, they will first take the corresponding lock out of the collection and then try to acquire it. If it can acquire it, it would update it. So notice that this pattern has the feature that even if a task migrated onto another thread where another task was running before, because these tasks can't acquire that same lock at the same time, this would be safe. Your physics would be correct. It does mean that these two tasks may be alternating the buffer inefficiently, which is not ideal, but at least you will get correct physics. So combining all of that and some other tricks and designs, what you get is a tables.jl compatible, really fast and lazy row iteration object. And then, as you can see here, we are reading quite some complex data structure out of them. These corresponds to a lot of nesting of unions of structs of stuff, a lot of that. So we can read all of that no problem. And the performance is, I would say, pretty good. Here we're comparing Julia implementation with mostly the C++ implementation. C++ implementation, but with like a table sort of interface, Python wrapper for the C++ implementation, and here uproot is like a NumPy based array at a time kind of operation. So what you're seeing here is the timing for one of the synthetic kind of workload for a physics analysis. You can see here, basically the point is that Julia is competitive with C++, and we scale linearly with respect to the number of threads before you hit any sort of other bottleneck like your disk or memory. All right, so that was the first part. So all I talked about will be equally applicable to both T-tree and R and tuple, but now I want to kind of talk a little bit about R and tuple specifically, because that's the upcoming new things. So what is R and tuple? So it is a brand new format for storing physics data at the LHC. And you can see that it has pretty competitive performance compared to industry formats. So I'll slow down a little bit because these two plots are a little bit busy. So on the first panel, you're looking at the throughput. So higher is better. Throughput of different formats on different file systems and conditions. What you're seeing here is that the RN2PO is way faster than the old T-tree. And it's even faster than some of the industry formats such as Parquet and HDF5. Of course, this is potentially a picked example for high-energy physics application, but still, these results are pretty impressive. And on the bottom, you're looking at essentially the compression ratio and how smart the whole file format is, such that when you read just a part of your columns, you want to touch minimum amount of bytes possible. So here you're seeing that RN2PO is the smallest format on disk, and also one of the smallest in terms of number of bytes touched. So the question is, how does RN2PO do it, right? Because you don't just go around and then think of a new way to encode really complex data and then suddenly it's good. So there must be some reasons. So I thought the best way to compare, to tell you why RN2PO is better, is to maybe compare and contrast the T-tree and RN2PO a little bit, because you can see where it's getting this improvement. So in T-tree, what you have is a situation where for every single column user sees, there is collection of storage corresponding to that single column. These two relationships are one-to-one. So now you might think, okay, recall some of the complex column I was thinking, telling you we need to encode, right? Now you have to cram all of those structures and metadata into these storage units. So that's not ideal, because you may have mixed data types and then they compress really terribly. Where in RN2PO, what happens is your user would see certain number of fields, right? That's your top level columns. But they actually decompose into more either storage units or more intermediate fields to encode the structure of the underlying storage. So if you are familiar with Apache Parquet or Arrow, this is the similar strategy over there. So I'm kind of happy that, you know, high-energy physics and industry kind of converged on what's best way to encode columnar data. So the key point here is that this would allow better compression efficiency and also makes your type schema composition much more uniform, because now instead of saying, well, vector has a special rule, you just say vector is, you put vector into another vector according to this type schema. So everything's much nicer. So the reading strategy for RN2PO is we basically parse the metadata for type schema, and then you process the referential metadata, which tells you where to attach the storage. And then you compose the Julia type, and then you kind of connect the types and the storage together. And then you would have your Julia table. So here, the most interesting thing is how do you parse and manipulate the type schema, because you're basically reading bytes from the disk, but then elevate all of them into your type space. So here we use multiple dispatch to modularly kind of handle each atomic container types. So here you're looking at a field that's representing a union, and then a field that's representing a struct. So we use these we use the multiple dispatch extensively to make individual parts work and very easy to debug, and then in the end they just compose because types. And then you can look at a real-world application. So this is a single column that you would read out from a real Atlas data format. And then so here you're seeing that, okay, so on the outermost you're looking at a struct, but then the struct has vectors in them. And then actually some of these referential data I was talking about have are struct of vector of vector of struct. So yeah, it's a little bit crazy, but the point is that we do push these schema to their extreme. So finally, let's quickly talk about how do we write RN2PO from Julia. So this is kind of it's a little bit work in progress, but we've made some headways. So you might think that because we know how to read these file formats, so which means we understand everything about them, how they works, the writing should be similar and easy, right? So actually, that's not true. In fact, almost no code can be reused from reading to writing. And then the reason is that if you recall the kind of the steps in reading, your information flow is you read the header, read the footer, parse them, and then you know where the things are, and then you just fetch them and connect them. But during writing, when you first write down the header and then the footer, you don't actually know where the data is. So when you commit the data to disk, then you would know the location of them. And then you have to go back to update your referential metadata. And in fact, it gets even more complex because sometimes user would open an existing file and then try to append the data to it. And then in that case, the new data might overrun whatever your footer is. And then so you have to move them and then find a new spot for them. This is even without talking about how do you have basically crash tolerance where you never leave the file in a broken state, right? So that's even more complex where you have to find new spot, but also keep old copy, stuff like that. So writing is actually the total opposite of reading, which is why it's complex. So the step 0 is to open the root file in a hex editor, because even though RN-tuple has specification, turns out not everything inside this root file / file system have. So we really need to understand every single byte in the root file, not just the RN-tuple, which we kind of understood. And then so after the hex dump, we have like a two-step strategy. For the parts that don't matter but are essential to keep the file legal, we just copy the blobs because we know what they do, but we don't really care how they're precisely constructed because there's no specification. For the parts that do have specification, we have real Julia objects and concrete I/O methods related to them that can write out an exact Julia type in the correct way. And then so Julia being a dynamic language actually helped immensely here because that means we can switch back and forth between using the stub and then using real Julia object and then compare the results on the fly to make sure I understand every single parts exactly. And the next step is to deal with the referential kind of information update. So we use a observables.jl-like structure, which keep a tab on where the metadata object was in the file. And then whenever anything needs to update them, they would know that they have to flush into the disk as a step. So there's some to-do list here. For example, the relocation is not implemented yet. And then also, if you have 2 layers of referential, currently it doesn't cascade. So it only knows one level of things. So these are to-dos, but they are not conceptually not understood. So with the current PR, here you are looking at, on the top, we writing out a RN-tuple onto the disk, which has 1 column of uint32. And then on the bottom left, we are reading it back from unroot.jl itself. Of course, we should be able to read our own data back. But most importantly, you can read it back from the C++ root, which is really important for integrating Julia into part of the high energy physics system because you're expected to use these to communicate with other people in the collaboration. So finally, there are some next steps in no particular order. We need to handle more Julia types, right? So this goes into the schema and schema generations. We need to be able to handle longer data and larger data and then allow these appending kind of usage. And then finally, we want to enable data compression. So far, it's not enabled because it makes the debugger harder. So these would make this whole thing much more usable to real life. And then just very briefly, the conclusion is that we have very robust reading for high energy data. And then the writing, we have a pretty concrete roadmap to achieve full interpolation, at least for RN-tuple. And then in fact, personally, I've worked on a Atlas analysis that's being submitted, and then there's another one going. So around these ideas, we have kind of organized the Julia HAP organization to help physicists to extract the physics knowledge from the vast amount of data at LHC much more efficiently and effectively. So yeah, so that's what I've been doing. Thank you.
Any questions?
Jerry, thank you very much for the nice presentation. If you can go back to the slide, I think it was 1 or 2 before. Yeah, here. The hexadecimals that you have will always be the same, or if they change, is it possible that they change and you need to update this?
Do you mean the...
In the upper part.
In the upper part.
Where you say call 1 is uint32 and then 0xCE.
Those are just dummy data.
Okay.
Yeah, sorry. This is just showing that I can write out some data.
Okay.
You can change the length of it, you can change the number of it.
Okay, so it's not, this is not what goes into your PR.
Yeah, so the API is you would have write rn tuple. First argument probably takes a file path or a sync, and then the second takes a tables.jl compatible object.
Ah, okay.
A dictionary of
Okay.
a vector is just simplest
Okay.
way to satisfy tables.jl interface. Yeah.
And one more question, if I may. Thanks. Apparently, you have to map the root types with your Julia code. How do you stay in sync in case something new comes in root?
So the neat thing about rn tuple is that it does not support arbitrary root C++ serialization. So before we had this problem where they would somehow serialize a C++ object, and then we have to reverse engineer how this somehow works exactly. In rn tuple, because it has a specification, everything they can write out without using like essentially a byte blob and then hack would be, we would be able to read them out exactly because it's a specification.
Yeah, for example, let's say they write a T vector in a root file and you want to read it. So if tomorrow they change it, they change something in the binary, representation of this object.
So when you go through the file serialization and read it back, it's basically like in arrow. If you think about an arrow, if you write an S vector into arrow or a normal Julia vector into arrow, they will result in the same thing, right? So when Python read it back, they just see a vector. They don't know what it came from Julia.
No, I care about the root object.
Right, so I'm not going to,
of root, not
right, so I won't be able to recover the root object because I'm not C++, but if the object was serialized using normal containers in the specification, I will be able to give you the correct data. Of course, if you want to recover the behavior, for example, a Lorentz vector has a Lorentz vector behavior, then either we would do C++ class name to Julia type metadata kind of thing, which is in the file. So you can see the class name as a string. So if you have a list of very common class in root, for example, Lorentz vector, we will have those built in because we also maintain the Lorentz vector stuff.
Okay.
Thanks for the question. That's a good question. Thanks.
Thank you. I think Chris has a question.
I have a kind of a comment that one cannot stress how important is that. If you haven't been using root, you don't know what you are dealing with. This is like really, he couldn't say that. This is a nightmare from 90s when the object-oriented programming was fashionable and everything is multiple inheritance there. There's all kinds of object-oriented nightmare which we dropped by the time. So it's really very difficult to do anything else than just to pull out the things that are really good. And this is the best part of root, is the super efficient files. This is like opening a whole new world for those who don't want to deal with the C++ from 30 years ago.
Yes, thank you for the presentation. I have a follow-up question on, because sometimes I think you, with rn tuple, you can support vectors and maps, std vectors, std maps. How you are going to deal with that? Because at the end of the day, you have to store something in the file. Then when the C++ will read it an std whatever.
Right, so that depends on, so rn tuple specification specs out what types they have, like a type ID correspond to what std object. We would have to basically dictate what kind of thing, how do they map to Julia types? Like, for example, map, right? So that would be what, a pair? Or a dictionary, right? So. Yeah, and then the union in C++, we would have our union, stuff like that. So we would have to spell it out, I guess. But I think most of the time, Julia has a superset of, in terms of the features. I'm not really, maybe the only weird thing in STD is STD atomic. But I don't know why do I need to know atomic in a file format, right? Like, so there's some questionable thing in the specification, but yeah. We will have like spell out what our types correspond to the C++ types.
Okay, well, thanks Jerry again for a wonderful talk. Really appreciate that.
Thanks.
This concludes the Scientific Data Media Symposium. I hope everyone liked the program. Hopefully we'll do this again at some point. I think the next thing in the conference is that we, I think maybe have a small break, and then we're going to go back outside to see the heavy machine construction demo there. So, okay, thank you again. And also, please thank our AV technician for keeping us going here, despite a little bit of chaos. So, okay, thanks again.